Hello, 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 hello.
Oh no? Okay. We'll figure it out.
Do you want
Yeah.
You want to set up an external monitor? It'd be nice with a no phone.
Yeah, if you can, yeah, but
Yeah, don't kill yourself trying to.
What do we have time-wise? Oh, we got a few minutes.
oh, okay, yeah.
Let's see if I can-
Test. Okay, cool.
Do you want to get set up with the mic?
Yeah.
Okay.
Which one plugs in?
Yeah, the HDMI.
This one?
Yeah.
Oh, perfect. Perfect.
So I'll introduce you guys, and then I'll get off, and then I'll give you the time markers, and then I'll pass over the mic,
Okay.
and orchestrate. Okay.
Sounds good.
Okay. I'm not sure why the.
Yeah, I don't know.
Asu just sent you like everything.
That's what I'm
She just
saying.
sent you like everything.
And I took a lot out for you, too.
You did, yeah.
Yeah.
Well, luckily those went.
Yeah. Let me try it. Is this Suntech? Still nothing? Is this mine?
Yeah, it's on.
Just did the microphone.
No, it's on. I have mine on.
Or you can do this one too.
Let me get all shit.
Test.
That's it. My God. It's like crap.
How do you do this shit?
start like putting the plushies out there so they can.
Down here?
Yeah.
Yep.
Leave them in these things or no?
Let me try it.
Oh, I usually just leave them in.
There we go.
Does it work here?
I'm risking it.
Risky. There you go. Let's start. It doesn't see it even on the.
Yeah, I love that one.
My camera just took way more than I thought.
Yeah, exactly right. It's always right when it's about to start when things don't work. That's how it normally goes, right?
Yeah.
Let's just try this adapter. I want to see.
Use the adapter right.
Here, try this real quick. There we go. Try that. How was this on and off?
Yeah, that's on.
Slide hot mic?
Yeah, hot mic and it's like you turn it on.
Yeah, thank you. Hello, everyone. Hope you're all having a great Saturday. Welcome to day 3 of SCaLE. Kicking off the cloud native sessions today, we have Justin Marquis and Christian Hernandez talking about GitOps, best practices, and using Argo CD. Let's give them a warm welcome.
Hi everybody, how's everybody doing today? My name is Justin Marquis. I work over at Acuity as a support engineer, also a Argo CD maintainer, and a local avid scuba diver. So today we're gonna bring you GitOps best principles using Argo CD. I'm here with my colleague, Christian Hernandez.
Yeah, so Christian Hernandez, I am an Argo CD maintainer, Open GitOps maintainer. I'm a head of community over at Acuity, and I'm a musician and guitar player. So for those who want to talk about guitars later, you can wave me down. Cool. So yeah, so we're gonna go ahead and get started here. We're gonna be talking about a lot of things today. We're gonna talk about like GitOps in general, how to set up your repository structure, talk about Argo CD components, talk about application sets, all these like kind of like best practices to like get up and running. Some of the things that you need to like look out for in order to get the most out of your Argo CD installation and your GitOps practices. So, and then we're gonna wrap up about how to get involved in the community, where to go, where to start, if you want to get involved in the community, and then we're going to talk about other projects we're involved with, talk about Cargo and what that gives you, kind of further expand like your GitOps journey there. So I'm going to talk about something that I can probably spend a whole hour talking about, and it's just GitOps in general, right? The GitOps principles. And so a little history about GitOps is that the term kind of came up early in the Kubernetes, I guess, journey. There was this company called Weaveworks that actually was set up as a cloud provider using Kubernetes and containers and things like that, and they lost. I don't know how many of you have. I have done this myself. Someone fat-fingered a configuration, and they took down all of US East 1, right? So basically half their infrastructure. Someone fat-fingered something. So what ended up happening is that, okay, let's recover, and like it took about 30 minutes to recover, and most of that was getting storage back online. So Alexis Richardson, being the CEO, instead of getting mad, he asked, "Whoa, how did we come up so fast?" Right? And his engineers, his SREs, were explaining the processes that they were using, right? Using Git as a source of truth, using a controller in order to reconcile things, and he goes, "Oh, this is kind of GitOps," right? And so GitOps started kind of like as this, idea or this way to describe kind of like how they were doing infrastructure as code with Kubernetes along with a source of truth. So later on it became more of like a practice, and a bunch of us got together from the Flux community, from the Argo CD community, people from Red Hat, people from AWS, right, all the usual big players, to start the Open GitOps project, right? So the Open GitOps project aimed to kind of put some principles around like what it means to do GitOps, right? And so we came up with 4 principles. First of all, like a system operated by GitOps is declarative, right? And so system managed by GitOps must have its desired state expressed declaratively, right? We have YAML and we have Kubernetes. So that is the declaration, right? There shouldn't be instructions on like how to do something, right? It should just be describe the end state. The second principle is that those desired states, those declarations, must be stored in a way that's versioned and immutable. This is where Git comes from. So the term Git, because Git is something that is versioned and immutable, right? Keeps complete revision history, that sort of thing. But it doesn't necessarily have to use Git, right? You can use things like OCI, you can use SQLite, technically, is versioned and immutable. And pulled automatically. So I always spend a little time on pulled automatically because people automatically think, oh, you're talking about a push versus pull system. No, not talking about that at all. Throw that thought away. I'm not talking about that at all. I'm talking about how the system retrieves those declarations, and it retrieves it in a pull fashion, meaning that basically separating it from an event-based system, right? You have an event-based system, right? Webhooks, some sort of triggers. All of that is something that shouldn't be relied solely on, meaning that you'll have webhooks, right? You'll have like an event-based system in GitOps, but relying on an event-based system solely is not GitOps. You need some sort of controller that automatically looks for revisions outside of some outside some sort of event. And so, and then the last principle is that it's continuously reconciled. So all of that happening, and it's continuously happening in a loop. So I always describe GitOps as as an air conditioning unit, right? As a wall air conditioning unit versus a central AC system. I remember straight out of college, my first apartment, I had a wall unit. It was awesome. It was the first AC I've ever had. Growing up, I never had an AC, so when I got my first apartment, I had a wall unit, right? And it was awesome. But it was something that I had to turn off and on, right? I had to, I got warm, that's an event. I had to get up, go, and turn on the AC. Once I got cold, that's another event. I had to stand up and go and turn it off. Whereas GitOps is like a central AC unit in my house today, where I set my desired state, right? I go up to the thermostat, I want it at 72, right? I like it a bit warmer. I set it to 72, and I leave it alone. And there's a controller, right? The thermostat constantly monitoring. If it gets too hot, it'll turn on the AC. If it gets too cold, it'll turn it off. So GitOps is basically the central AC unit with the thermostat. You set it once, and there's a controller monitoring there. There's no longer an event. I could do an event. I'm like, you know what, I want the AC off, right? Like, there's obviously events, just like in GitOps, right? There's events that you want happening, but I don't rely solely on those events. I have a controller helping me out. And that is the gist of GitOps. So, and so that, now talking about GitOps, now there are tools that do that for us, right? We have a bunch of YAML. We're managing a Kubernetes system. We want that YAML to be deployed. And so we store that in Git, and then we have a controller that monitors changes, right? Whether it's a change in your source of truth in the Git repository, or there's a change on the system itself, right? Someone does an out-of-band change, right? I go in and I delete a deployment, or I change the replica count. The controller will then look at your source of truth and then switch it back. Or if the replica count changes in Git, it would change the system state. And so there's tools out there now that do that. Flux was one of them, and Argo CD is another one. So Argo CD is a open GitOps compliant tool for Kubernetes. So with that, I think Justin's going to go over some of the components of what Argo CD is.
How many of you out there are currently using Argo CD? That's a good number of hands. How many of you understand all the controllers and how they work together? All right, that's perfect. So let's go ahead and go over that. Here you can actually see the controllers here. Here in the center there's the core controllers. These are your main controllers that operate the Argo CD. You also do have the API server, which interacts with the CLI, gives you the beautiful UI everybody knows about. But here in the middle, the core, these are going to be our most interesting controllers, and we're going to start here at the core, the heart, the application controller. The application controllers there, it's responsible for looking at the live state of your cluster and the desired state and reconciling those differences. While doing so, it does manage and establish a watch on all resources on a cluster that it's looking at. So it's a very powerful controller. It is the heart. Whenever a change is detected in Git, that's the repo server's responsibility. It's going to go out, check that. Application controller is going to reach out to the repo server and say, hey, are there any updates? Repo server will respond back saying yes or no. If it is yes, the application controller will take those manifest and then reconcile the difference. And that's basically how that works. Down the lower, we do use Redis just as caching. The UI is pretty heavy when you have a lot of resources. Rather than having to keep reconciling that, we do store it in cache to improve speed performance. We're going to start off with some basic installation recommendations. Here at Acuity, I work with large corporations, small corporations, and I just kind of want to share the best practices that we see. A lot of people, they ask us, should I use the Helm charts to install Argo CD? Should I just use the customized charts? In the end of the day, it really doesn't matter. It's what works better for you. Preferably, I like customize. I've seen installations where customers run in nearly 50,000 applications and they're using the basic customization charts. The Helm is slightly opinionated. When you go to upgrade Argo CD versions, if you want to stay to a minor release, it's much easier if you have the full power with the customized charts. Talking about sharding. A lot of people ask about sharding. When should I start sharding? Sharding, if you're just deploying to a single cluster, you don't need it. If you're deploying to a lot of clusters, let's say 100 or more, you're going to have to enable sharding so you can distribute the workload for the application controller. Typically, when you start managing a cluster and you see it's managing around 70,000 resources, you'll start to see some performance impact, and then you might want to think about possibly scaling up and enable sharding. When you do start scaling, the repo server scales very well. It's responsible for reaching out to Git, generating those manifests. It requires a lot of CPU, a lot of memory when you start generating numerous manifests. So you can see here I scaled using customize to 4. This scales up real nicely. You can increase that as you need, and as the metrics start showing you that you need more work. The next thing people have a question about is the status processors and the operation processors. The application controller basically has 2 queues. Oh, yeah.
Yeah. There you go.
How's that? All right, thank you. So basically, the application controller has 2 queues that it performs work. It's a status processor, and then the operation processor. Basically, the status processor is responsible for updating health checks, checking the status of the application, if it's out of sync, if it's in sync, and then you actually have the operation processor, which is responsible for performing kubectl apply. By default, the status is set for 20 workers and 10 workers for operation. Typically, when you start deploying in the high hundreds of applications, you need to start increasing these. It basically gives more workers to the controller and allows it to perform more responsibilities. And another one that we highly recommend. By default, if you have a self-heal function enabled, which basically the controller's watching the resource, if something changes that it's not supposed to be in the desired state, within 2 seconds by default, it'll go ahead and do that. We found that increasing this anywhere from like 300 seconds, from 2 seconds. If you get an application that's either misconfigured or you have some sort of mutating webhook that makes a change to the resource, the controller gets real angry and it starts fighting. It tries to reconcile that difference. It's saying, this is the desired state, it's not the desired state, and it gets in a loop. And it starts using up CPU and memory as well. And you start seeing performance impact. So this setting right here for the self-heal timeouts, adjusting that gives you a lot more flexibility.
Yeah, and just a quick note on that. Like, so when I talked about GitOps being, like, you're going to have event-based things set, right? Like, so someone's like, well, why would you set the reconciliation timeout like higher, right? Don't I want it constantly checking? Well, like, you're going to get performance issues. So that way, now you have a way to tune the timeout on when the reconciler runs, and then, but you can also have your event-based thing. So you'll definitely have both.
And coming from there, starting off smart. By default, Argo CD comes with the default project enabled, which gives full permission to deploy to any cluster, use any repository, don't use it, turn it off. Start taking advantage of Argo CD projects. Argo CD projects basically enable you to logically separate your applications. Using single sign-on, you can break it up to different teams. Argo CD's a full multi-tenant platform. So you break it up, use single sign-on, don't use the default project. Just as an example here, you can actually see this is how you would restrict the default project. basically you're not going to allow any source repos, any namespaces, any of the destinations of any resource. Just restrict it. As an example, this is another application or app project we created here, which you can see it does allow you to deploy any type of cluster resource, but it's restricted to the in-cluster, any namespace, and then it specifies a specific list of repos that are allowed to deploy. If you try to deploy anything outside of this within that project, you cannot. So please disable the default project. Don't use it. It's only there basically for onboarding, learning Argo CD, and making it easy to adapt. And the last recommendation here on installation is actually using the app of apps pattern to actually have Argo CD self-manage itself. I do run into a lot of people, they're still using kubectl apply to upgrade Argo CD. When they already have Argo CD on their cluster, use it itself, let it manage itself. It's real easy, and it's just a simple app. And I'll hand it off to Christian.
Yeah. So, so I want to spend some time talking about Git and repository structures and things you need to keep in mind. Git's going to be very, very central to what you're doing in GitOps, what you're doing in Argo CD. So anything that you do in Git, Argo CD is basically gonna do what you tell it to based on Git, right? So when I talk about repository structures, people say, okay, well, I'm using Argo CD, I'm getting started with Argo CD. I have a large team, I have many teams. Like, how do I set up my repository structure effectively in order to, take advantage? Like, what is the best practice there? Like, what is, give me a template, right? Is usually what people ask me, right? Like, just give me a template. And I go, unfortunately, I cannot, because repo structure is dependent on something called Conway's Law. Who's familiar with Conway's Law? A little bit. Okay, so for those who didn't raise your hand, Conway's Law basically is it says you design your system based on your organization's communication structure. So basically, repository structure in GitOps falls in that same category, right? I can give you a template, but if it doesn't work for your team, if it doesn't work for your organization, right? Whether your organization is very, very siloed, whether there's concerns in terms of regulatory concerns where no, people can't access this and you need blah, 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 right? There's just a slew of things to take into consideration. So there's no kind of one true GitOps repository that works, right? It's just impossible. Because of Conway's Law, right? It's going to depend on your organization, right? GitOps is basically Git workflows. So how your organization does those Git workflows is going to affect your repository structure. So that being said, it doesn't mean we leave you, I guess, all puns intended, high and dry. But there are some basic best practices, right? And the first one is dry, right? Don't repeat yourself. It's kind of generically, you have all this YAML you want to deploy, and you have all these environments you want to deploy that YAML to, and the variance between environments is maybe 1 or 2 lines, right, of YAML, right? So instead of connecting to this database, you connect to this database, but the rest is the same, right? The delta between the two is very, very minimal. So, but that doesn't mean you have to copy the same YAML and just change one line, right? You can use things like what we talked about before, Helm, right? You can use Helm to not, templating to not have to copy and paste a bunch of YAML. You can use Customize, right? You can patching framework like Customize. You can use what you like, really, in Argo CD because of the plugin mechanism. Like you can use YTT if you like. You use a JSONet. I think people still use that. And so, whatever works out for you, whatever, basically don't repeat yourself, or I like to say don't repeat YAML, I guess, because it's kind of a pun there for Kubernetes users. Also, you're gonna separate your source code source code versus the deployments that deploy that source code, right? So, and the reason for that is there's just different life cycles, right? Coding life cycles. There's software engineers or whoever's coding, are making constant changes. They're constantly iterating from the application, right? And if you have a team, that's even expanded even further out than that. So whereas YAML or deployment of that of those things actually have a shorter, or it doesn't change as often in terms of deployment, right? And so you know, being like an SRE, right? Like you can just imagine the source code repository constantly changing, and you're like, well, is that touching my environment? Is it not touching my environment? And you have to, there's workflows that you don't care about. So those are two separate workflows. Those are two things. It's like, don't just kind of just separate your source code from your YAML, because you are promoting manifests versus promoting code, and there's just completely different life cycle, right? And so those are kind of just some of the things that you talk when you talk about GitOps and, like, you know, where to get started. Right, let's separate the concerns is one of them, right? And use templating, right? So in order for you to get the most out of your YAML, right? And so people ask how many repositories. It's like, well, like, you know, okay, should I throw everything in one Git repo, right? Like, so my environment is just in one Git repo. Is it many Git repos? Is it X, Y, Z, right? So there's really kind of like two schools of thought, right? So one of them is what we call a mono repo, where people mostly start out here. And so I have a sample Git repo here, but basically what you're gonna do is that you're gonna have a mono repo, meaning like I'm gonna have everything in one repository, right? So mono repo means something else to coders. So I'm talking specifically with GitOps, there's a mono repo aspect of it. But like there's things like, all right, I'm gonna have all of my components, right? All like the Argo CD specific things in a specific directory structure. I'm gonna have core components, right? Like configurations, things that what we call cluster add-ons, which we'll go over in a bit, and any of the tenants that are in your environment, right? Like these might be application deployments, these might be teams, it might be, you know, sort of, you know, one things that that belong on the cluster, but you don't necessarily, it is, as an administrator, you don't necessarily deal with a lot, right? They're just tenants on your cluster. Whereas these other things that are separated by other directories here, those are kind of maybe things that are, as an administrator, you interact with a lot. And then I have, I always have this bootstrap, right, which I think we're going to go over app of apps in the next couple slides. But I have a bootstrap directory, right? It's kind of like the chicken egg thing. Justin was talking about Argo CD managing itself, but like, how do you get it to that point, right? Like, how do you get Argo CD to manage Argo CD without having Argo CD installed? Because then you need Argo CD to install Argo CD, right? Like, there's this like whole thing. So I always have like this bootstrap kind of point of entry, because this, as you can imagine, can get kind of big. It can get, especially with a lot of clusters, with a very, very busy system. You want a way to be able to deploy everything with one kind of command, essentially, is what that bootstrap directory is for. And so, another way of doing it, and this is kind of like what I settle on, or what people settle on later on after they've been using Argo CD for a while, and, you know, the organization grows, is I like to call them polyrepos, but basically it's many repositories, Git repos, depending on, you know, what the thing is for, right? And so this is kind of, this pattern is actually something that they use at Intuit, right? And so at Intuit, they do minimum 2 repositories, right? One, what we call a control plane repo, which is basically all the things that you need in order to get the cluster up and running, things that are configuration for the cluster, things that basically is like, you know, you have a naked Kubernetes cluster with nothing on it. Where do you start? That's the control plane repo. And what we call a control plane is like, that's your point of control for that cluster, right? That this is where like the admins live for that cluster. This is kind of like their repo, and this is like their point of control. I have, this is like very, very bare minimum, right? Basically, it just installs Argo CD and that's it. But I set it up similar to that other repo where I can start adding things, right? Like I have a directory called system, meaning like what are the system components, right? Argo CD, maybe I want to install KubeVirt, things like that. Configurations live on their own. And then I have a bootstrap basically to kind of, as you know, you can see here, when I install this, I target the bootstrap directory. And so, so that's one repository for this one cluster. There's 2 repositories then. Then you have an application repository, which is basically just a repo with the deployments, right? Like here, we're using customize for overlays, right? Depending on what I'm going to do, EKS, GKE, I have a default, right? And so this is just deploys the application components. So if I go back here, and I go to base, like this is a very simple example of a deployment and a service, right? All of that. So all just kind of just what deploys this specific application, this Go blue-green application, lives in this repository. So then basically I kind of hand off the responsibility to that team, right? It's like, okay, you manage your deployments and repositories and things like that. And then, you know, whenever you're ready to release something, tell me what tag it is, and I'll switch the tag, and then we'll do a release that way. So kind of like a high-level overview. So other things in terms of repository structure, Git workflows type of things, is that GitOps workflows, there's an instinct of people who have done Git workflows to use Git flow. Basically, it's like, oh, I'm going to have a branch for dev, I'm going to have a branch for stage, and then when I'm ready to upgrade from dev to stage, I'm just going to merge those branches. And like in GitOps world, that does not work. That never works because the difference between dev and stage isn't the deltas between the two, because in dev you may be connecting to a dev database, and in stage or production, you're connecting to the productions database. So like that merging is just never going to work, right? Like you just can't simply merge those branches. So don't use Git flow. Use something called trunk-based development, right? Basically trunk-based development is you have a single trunk main, right? We just call it main. It doesn't have to be main, but you have a single trunk of main, and you have short-lived feature branches or release branches, meaning that, okay, I'm going to make a change in dev, make me create a branch, make my change, submit a pull request to that, to the main branch, and then when that gets merged, then the GitOps controller deploys it. How you control what gets deployed is based on these, I don't think I have a good example here. I'll just do this here, overlay. So here, instead of clusters, it can be environments, right? These directories can be called a dev, stage, production. And so when I make a PR, I'm going to change the things in the dev directory. And then once I merge it, then it gets automatically deployed to dev. So, so I would, trunkbaseddevelopment.com if you're unfamiliar with trunk-based development. But the idea is you have a single trunk and short-lived feature branches that always get merged back into the trunk. Rendered manifest. So the rendered manifest pattern basically is a way to, let me make this a little bigger. So when you store something in Git, either it be Helm, whether it be customized YAML, Argo will then take that and it'll run customized build on the fly at runtime. It'll run Helm template and then deploy that Helm repository. So Argo actually takes what's in Git and then it will actually render it out to the Kubernetes cluster, right? This is fine, and this is it even scales pretty well if it is, as Justin was saying, if you're like tuning the repository controller and things like that. But if you want to really get the most out of your Argo CD installation in terms of performance, we do something called rendered manifest. Means the rendering happens before Argo even touches the YAML, right? So for example, Helm, right? Helm template, right? It'll just spit out the YAML. Instead of Argo CD doing that, you do it, right? And then it ends up looking like this. You do it actually in CI. You push that to CI. So what ends up happening is that you make some sort of change in your Git repo. There's a CI system that does the rendering of it, right? Either the Helm template or customized build, and then it'll store that somewhere. And then Argo CD will then pick it up and deploys that as is. So what that buys you is you save the compute, the memory, CPU, from Argo having to do that. And in a very, very busy system, that repo server can get really overloaded actually pretty quickly. And so this is just something you can do in terms of tuning and performance that will make Argo CD faster. So again, I could probably do a whole presentation on rendered manifests. There's a bunch of them out there. And then there's, if you're using a mono repo, right? So if you're using a single repository, there are scaling considerations. Basically, the repo server is something you need to look for because anytime someone makes a change, the repo server is going to kick off. Even if there's a change to one app, it's going to affect all the other applications, just because you need to. The repo server needs to re-download, right, those things, right? And so there's a cool pro tip. I actually I didn't know about this until Justin told me, right? And so when Argo CD runs, I think, a Helm template, right, that's a serial process. So if you have like hundreds and hundreds of Helm deployments, thousands of Helm deployments, they wait in a queue, essentially, because it's a single process, right? And so a pro tip is to turn on concurrency, meaning like let's take advantage of all those threads we have on these computes nowadays, right? We don't no longer need to do serial processes, do all these in parallel. I believe in Argo CD version 3.0, that's going to be the default. So I just found that out today. Thank you, Justin, for telling me. That's going to be the default. So this is, hopefully, this is not something you should need to worry about for too much longer. So I'm going to talk about a little bit about what an application is, and then I'll hand it over to Justin. But what an Argo CD application is like, so we keep talking about applications, deployments, right? So how does Argo CD deploy this? And it deploys this with a CRD called an Argo CD application, right? And so what an Argo CD application is basically a unit of work it's the smallest atomic unit Argo CD uses, meaning that you give it a source, right? In this instance, we're doing a Git, right? A source can be a Git repository, a Helm repository, pretty soon an OCI repository, so stay tuned. And then you give it a destination, right? So a destination is basically a Kubernetes cluster with a namespace, right? And so, and here we're deploying in what we call in cluster, right? That's the shorthand version of saying deploy these YAMLs in the same cluster that I'm running in. And you give it a namespace, and it should be able to, it'll deploy it then. So something to remember, this is a one-to-one in terms of source or sources, and we'll talk about sources in a little bit, to cluster, meaning that you designate which cluster it installs on. For this example application, if you have 3 different environments, you're going to have 3 different application definitions. So it's a one-to-one. Just something very important to remember for Argo CD applications is a one-to-one relationship between source or sources and destination. So it's pretty flexible, right? So there's things that you can do, like sync policies. Some of the sync policies that I always turn on is auto sync, right? Sync policies is automated, and I always turn on pruning. You may or may not want that. What I always do, so pruning basically means if it's on the cluster but it's not in Git, I'm going to delete that. So meaning that's like, I like to call that the true GitOps, right, kind of switch. It's like if it's not in Git, I'm deleting it. So if anyone adds anything to the cluster, it's going to get deleted. You may or may not want that, right? You can flip that switch, right? So you can turn off pruning. In some cases, you do want to do that, especially if you have outside controllers adding things like storage. You definitely don't want storage to get deleted. Self-heal, I always turn that on. Self-heal is always true, meaning that like if there's any divergence locally, right? Meaning like if it diverts from the source of truth, someone scales something up, you want it to revert back to Git. And so finalizers, right, is another thing. So finalizers, adding a finalizer also is another true GitOps switch, right? So if you don't have the finalizer, what Argo CD does when you delete an application, it'll just delete that definition, but it'll leave the resources on the cluster. But if you have the finalizers on, that's like, again, another true GitOps type of way. If you delete the application, all the resources is referencing, it'll also delete those on those applications as well. So it'll also wait for those things to delete. So it'll, when you delete an application, it'll start the deletion process. It'll first delete all the resources, and then the application will finally get deleted, right? And so now I think talk about extending application. I'm going to turn over to Justin. Talk about what you can do beyond just like setting the definition of an application.
Thank you, Christian. So let's take a look at, you can see this application that's listed right here. This particular application is referencing the path you can see right here, apps. And what you can do is take an Argo CD application to point at one or more or a series of other Argo CD applications. So basically, the root app is the parent, and it deploys child applications. So if in Git you check in another child application, Argo CD automatically adds it to your cluster. What we'll do is we'll take a quick example here using the app of apps. And you can see here in the apps directory, I have 3 different apps. This is actually an app of app sets. We'll talk about that later on. And an application for Argo CD and an application for Cert Manager. So I have a Bootstrap app that we saw earlier, and it takes the path apps, deploys these 3 resources onto the cluster. Argo CD picks them up, sees the custom resources, then creates those apps as well. So it's real useful when you want to scale out. If you have a bunch of cluster add-ons you want to add, you can logically group them in folders and have it done all at once. So it's a very, very useful feature. Next, I want to talk about Helm inline values, the do's and the don'ts. Christian was talking about config management plugins, how Argo CD has it built in, Helm, customized, JSON.NET, and it could be extended. By default, Helm has quite a few options. In particular, when deploying a Helm application through an application's custom resource, you could do inline Helm values rather than specify a values file, or you can also specify parameters, which parameters take override. But I've seen it in the past where customers and other people are using inline Helm values improperly. Sometimes they'd like to deploy hundreds of these. Please don't do that. Use a Helm values file. What ends up happening here is if you do a bunch of Helm inline values, the values actually get stored in the application resource under the status field. And when you have pages of this with the reversion history, this CR gets huge, and it starts impacting performance. So if you're going to use Helm inline values or parameters, my best case of advice is if it doesn't fit on one page and you have to scroll down, you are doing it wrong. Next thing we're going to talk about is multi-source applications. They were introduced in Argo CD 2.6. This was a huge, huge thing the community wanted. Basically what it does is it allows you to target multiple sources, whether it's a Git repo, Helm charts, and then what it does is it combines those resources, renders them down, puts them into one file, and then applies them. This gives you the ability to deploy applications. In this example, we have a billing app, and then we have a configuration in another Git repo. So basically, it combines them, generates the manifest, and combines them in one source and into one app. So that makes it nice. Another way of using multiple sources is using external values. Let's say your Helm values live outside of another repo. You're able to do that now. Here you can see the repo URL at the bottom. The second source is actually just referencing a list of files in Git, takes those values and applies it to the next source as actual Helm values. A lot of people are doing this. Kind of a guideline when using multiple sources. If you're using more than 2 or 3 sources, you're probably doing it wrong and you need to rethink your strategy. It's not designed to have 5, 6, 7, 8 sources. There is a performance impact not only on the application controller, the repo server, but also Git. Especially if you're self-hosting it, you will start to see throttling. And then that brings us here to application sets. We've been defining applications here. Doing it by hand is time consuming. The old way of doing it was the actual Helm template applications, and everybody kind of had their bespoke process of how they were creating it, and the folks over at Red Hat came up with application sets. Application sets, basically, it's a powerful templating tool that generates Argo CD applications for you. And how does it do this? It has another controller called the application set controller. And its job is just to create, update, and delete application resources. The controller's only job is to ensure that the application resources are consistent and defined within the parameters of the application set resource. What does that mean? Basically, when you create or delete an application set resource, the application set controller responds by creating, updating, and deleting Argo CD applications. It doesn't modify or delete any sort of Kubernetes resources, only the application resources themselves. Typically, it's recommended only by default. This is like an Argo CD admin tool. There are some exceptions, but it's going to be outside of the scope of this talk. If you want to take it and talk in the hallway after, I'm more than happy to do that. We're also going to go over some safeguards. So how does an application set work? It has a tool called generators. And these generators, there's 9 of them right now currently. I have the 4 listed that are the most popular, the list, cluster generator, the Git generator, and a matrix generator, which allows you to combine one or more. What are generators? What do they do? Generators, basically, they're responsible for generating parameters that are later applied into the template field of an application set. Let's see an example real quick. So this is a guest book. This is the simplest generator there is. Usually this is the best place to start when learning application sets. You can see here the list generator has a list of elements, starting with the name prod, namespace, guestbook dev, and then below it there's the dev, guestbook dev. What the list generator is it takes these parameters. Make it a little bigger. Yeah. Is it a little bigger? And in the template field here of the application set, you can see we have defined namespace. So basically that parameter is then applied and it creates that application. A lot of people ask too, like, once you apply these, since it's an application set, it's not an application, it actually doesn't show up in the Argo CD UI. So the community's got kind of creative and we have a term that's called an app of app sets. And what an app of app sets is basically just an application pointing to where your application sets are stored in Git. And what that looks like in Git, allows you to have a little bit of visibility, is you can actually see the root application here, which shows the application set, and then you can actually see which applications were created from that application set. So that's a little pro tip there as far as seeing visibility on application sets. I know there's a lot of requests in the community to make application sets first class in the UI. It's still being worked on, but that's the way around that. And let me go bring this up. Next, we're going to talk about when using generators. You can also use for post-processing selectors. This can be either match expressions or labels. So if you're using a generator like this here, you can see the key name. The key is the name. Operators in, values are only in prod and environment. If I remove dev down there in the values, it will not create the application set using these parameters at all. It'll just completely negate those. So this is really useful when you're using like a cluster generator, which basically takes labels from all the clusters that you're deploying to. A lot of people, it's really neat, if you actually label your clusters in Argo CD, you can use then application sets based on those labels to decide what type of applications you want and manage your add-ons. And then, go to the next one. And these are the application safeguards I recommend. As I stated earlier, if you change something in an application set, it's going to apply and update by default. So there's a couple safeguards you can use that you should be aware of when using application sets. The first being preserve resources on deletion. If you add this into your application set under the sync policy field underneath the spec, preserve on deletion, basically when the application set creates the applications, it's going to add the finalizer that Christian talked about earlier. And if you make a change and that application gets removed, all your resources get removed as well. I've seen this where somebody made a change, they weren't aware of how the application set controller worked, and their prod instance went down. They were unfamiliar. The other safeguard here is the sync policy. By default, it's set to sync, which allows the application controller to create, update, and delete all applications. There's some other options, create only, create update, and create delete. Each of these are useful using different type of generators. Specifically, like using a cluster generator, it's real nice to just do create update along with the preserve resources on deletion. Very useful. If you have any more questions, please reach out on that. And I'm going to hand it over to Christian to talk about cluster add-ons.
Yeah, so cluster add-ons, I mentioned earlier about the when you have a bare Kubernetes cluster, right, and you bootstrap it with things that you need in order first to control that, right? So that's why I have like the control plane repo, and then you have the application repo. Well, there's also additional things that you want to add to the clusters, what we call cluster add-ons, right? So these, when we say cluster add-ons, is basically functionality that most, if not all, your clusters are going to need, right? So at a minimum, you need a cert manager, the external secret operator, right? There's a lot of ways to manage secrets at Acuity, and I think most people at the Argo project are pretty bullish on ESO, right? Because it's just so flexible. And so you're at a minimum going to need that, and then some sort of policy enforcement like Kyverno, something to enforce security constraints on your clusters. Recommended, right? Not always needed, right? Depending on what you're doing. You need some sort of traffic manager, service mesh. You're going to have that there. Some sort of storage controller. If you're going to do multi-cluster networking, that's like something else that's considered a cluster add-on. And for things that I'm working on, these cluster add-ons are usually deployed either by like a Kubernetes operator or like a Helm, some sort of Helm chart. And for things that I do, these things are usually part of the control plane repo. Actually, what larger organizations do, like very large organizations like Intuit, they actually have this in a third repository. So, so if you're thinking about like large enterprises, you're going to have a minimum of 3 Git repos per cluster or per environment or per Argo CD installation, however you want to say, but it's going to be at least 3. I have it part of the control plane. For most people, that's probably fine. And that probably makes sense. Makes sense to me. But it's sometimes it's in its own Git repo. So so I kind of just wanted to make a quick note about cluster add-ons. And so since we're running low on time, I'm just going to fast forward real quick on how to get involved. Right, so how to get involved in the Argo project. So the Argo project is a CNCF graduated project, and it's actually the third largest project in the CNCF, right? Only Kubernetes and OpenTelemetry is larger, right? So that's kind of cool to say that. It's actually the 4th, since we're here at SCaLE, it's the 4th largest project in the Linux Foundation in general, which is kind of cool, a little humbling to be said in the same breath as the Linux kernel, right? And so it's really, really large, really, really popular, and it's a really, really large community. So So the best place to get involved is to go to that link there. We put a QR code just to make it a little easier. Basically, attend meetings. If you are, we have weekly meetings specifically for Argo CD, Thursdays at 8:15 a.m. Pacific time. So I'll let you do the math if you flow in from somewhere else. Jump on in, listen, all the lead engineers, maintainers, mergers, all the folks who are decision makers. Actually, we do meet regularly, weekly, to talk about the next releases, what features we want to put in, what bugs there are. People bring up issues, right? And so in any open source project, any open source project, the last bullet point is true. Best place to get started if you want to start your journey in contributing is documentation, contributions is always sorely needed. It is no different in the Argo project. There are tons of, like I see things that are wrong or could be better in the documentation all the time. My fly swatter, my bandwidth does not let me get to all of them, so probably most is true. So if you are, if you're not necessarily a coder, right, if you're more like me, like on the operations side, right, like is shaky at best, but documentation is always sorely needed. That's I want to say if you want to get involved, that's the quickest way for you to be a hero, not only in the Argo project, but in general. So I don't know if you wanted to add anything else on it. All right, cool. The last thing I want to talk about is what's next in Argo, right? What's in terms of Argo and GitOps. I'm running a webinar to talk about GitOps promotions, right? And so I'm gonna leave this up here for a little bit, but I'm part of a project, Justin and I are part of a project called Cargo, separate from the Argo project, but still open source. I'm gonna be talking about something that I call continuous promotion and how CI/CD needs to evolve now to take advantage of things like Argo CD, things like GitOps, right? And just GitOps in general. So I'll be talking about Cargo, what it is, how it fits into the whole GitOps story, how it expands, and I could definitely do another hour of just Cargo by itself, which I will do. So go ahead and check that out if you have time. And I think with that, do we have any time for questions? You got like a few minutes? Okay, okay. So we have, so thank you. Any questions out there? By the way, before you leave, there's plushies, stickers. If you are an Argo fan. Yes, question. Yeah, Argo 3. So Argo version 3.0 is due out in May 5th. So may the 5th be with you, or may the 4th be with you. It's going to be deprecations, right? So things that we've deprecated but are still in the code are actually going to be removed from the code. So there is a list of breaking changes that we have on the documentation page. The biggest feature is going to be OCI support, native OCI support.
Any other questions?
Any other questions? Oh, there's a question there. Oh yeah, on the thing. Yes, yeah, we're gonna post it. Yeah. Yeah. Yeah, I don't know.
Are there any like best practices for mono repos that have a high volume of changes to a manifest repo? Like in my personal case,
okay, yeah.
it's exceeding the rate limit of
Yeah.
our Git provider.
Give me 1 second.
Okay.
Oh, perfect. Oh, no, that's great.
Very familiar with cloud native
Okay.
ecosystem.
Yeah.
Just let me
Awesome.
know.
Yeah. Yeah. No. Yeah, I'll give it to Justin here. Yeah. Awesome.
Yeah, great
Yeah.
presentation.
Okay. Thank you. Yeah. Sweet. All right. Are we good? Sweet. Yeah.
Hello. Hello, world. Great. Can you hear me now? Yeah, 12:30. Yeah.
Check 1, 2.
Check 1, 2. Check 1, 2.
Is there a way to mute this or just turn it off and on?
Hello, everyone. Hope you're all having a great Saturday on day 3 at SCaLE. On the second session of Cloud Native track here, we have Scott Williams with us here to talk us about scalable open source data science on bare Kubernetes bare metal clusters. Take it away, Scott.
Thank you very much. I have a QR code here, and so on the next slide, if you want to download the presentation, if that's easier for you to follow along, if the conference Wi-Fi will allow it, you can access the slides, and there'll be another one at the very end as well. So my name is Scott Williams. I am a Linux DevOps engineer at the University of California in Santa Barbara. And I'm also a Fedora ambassador, so you might have seen me over here in the Fedora booth at the Expo Hall. That was me last night with the QB shell with the floppy drive. I've been doing containers since around 2015. I think it was actually Justin Garrison that told me about Docker way back when. So the containers and Kubernetes isn't a new thing to me. I've been doing it for a while, but this is part of the adventure specifically at UC Santa Barbara. I started at UC Santa Barbara in March of 2021, so about 4 years ago. So for the scope of this talk, this is a high-level journey, how we went from public cloud to on-prem bare metal Kubernetes, which is a different trajectory than I think some of you might have had before. This is about the tooling and the workflows that supported that. And some of the things that we learned along the way, there are different challenges and opportunities that come along with such a move like this. But here's some things that we're not going to talk about. I'm not going to talk about why any one vendor is better than another. This isn't a sales pitch. I'm not going to sell you any licenses for anything. I have no free credits to anything to give out. So. And also not in the scope, I'm not talking about setting up a data center, so if you don't already have a data center, I will not be helping you set that up from scratch today. So we do data science, and one of the major vendors for data science is Jupyter, and Jupyter is open source. And if you've done much with data science before, like machine learning, or you've done course environments, you've probably interacted with Jupyter at some point. And so the two most common ways to interact with that are through a Jupyter Notebook and a Jupyter Lab. And those are different user interfaces for an interactive Python, and then you could save those in a particular file that you might store in like a Git repo, and you could share that with others, and so others can clone your interactive Python and carry on what you've done with that, or review it in some way if you're doing research. And it's a way to debug this in an interactive way, and it's a very common, ubiquitous tool, especially in higher ed. RStudio, there's another, Erlang is a common language that is for data science, but underneath Erlang is a lot of C and C++ and Fortran. And I heard there's a Fortran talk here, and I'm sad I missed it because this has suddenly become part of my day job. To deal with Fortran now as a DevOps engineer is really fascinating. It's like, how did we get back here in my life? So Erlang is a very powerful tool that also comes with some really interesting challenges to support. RStudio is its own graphical IDE that supports Erlang. It's an AGPL project, and Jupyter also has its own Erlang support with R Notebook. So these are two different R interfaces that we support at UC Santa Barbara now. And Jupyter Hub, find that a lot of people maybe have used Jupyter Notebooks before, but maybe haven't used Jupyter Hub. And so this is a way that it's all in a browser. It's a web interface that provides a central entry point and RBAC, so it's multi-tenant, multi-user for Jupyter, and it can also do RStudio environments through an RSession proxy. And this explicitly runs in Kubernetes. This is a Kubernetes thing. But this solves a lot of problems for us, because if you have like a shared environment, you're doing like a Citrix or Parallels kind of thing, someone updates their dependencies and causes a lot of fires in the rainforest, so to speak. So this is a way that we could have an image-based way. It's a lot harder to break stuff in this environment. And you're also, this is just anyone with a browser, even a mobile phone can use this. You don't need to have some kind of thick client. Just for definition's sake, what is bare metal Kubernetes? So this is Kubernetes running directly on the server hardware. So we don't have like a VMware going on. We don't have, it's not running in public cloud. The Kubernetes nodes themselves are running directly on server hardware. In our case, it's running directly in our own data centers. So is it still cloud native? So it's kind of a funny thing if I'm talking about going from public cloud to bare metal, is this still the cloud? And that depends on your definition and practices. So I figured it would be best to follow what's Google's definition. Cloud native refers to how applications are built and delivered rather than just where they are deployed. And in some cases, an application may not even run in the cloud. And if you'd like a quote, you can scan the QR code. That'll take you to the Google documentation for that quote. So it's more important from a DevOps perspective how you're running things than where you're running them. This isn't a new concept, right? This has been around as part of the cloud native and DevOps talks for a while. So we kind of have a story of two major iterations of our Jupyter Hub experience at UC Santa Barbara, that it's not just a matter of where they were running, but how they were running. The tooling and the concerns were very different between them, and also, frankly, the cost was very different between them. And we started out on Google Kubernetes Engine, GKE. So we'll talk about that part of the journey first. And then we got popular. People started using our service more. This is a good problem to have fundamentally, right? It means that your stuff is working at some base level. And but the other thing with cloud is the costs tend to scale with your growth. That's part of the business model, right? So even with cloud best practices, you know, there's still quite a bit of money to sustain that. So we support over 51 courses and over 4,600 plus users a year. And so when I say that 4,600 users, if you're used to DevOps in the sense of a regular web application, you're counting unique visitors. That's nothing. Put that in a lame stack. These are people that are actively running compute workloads, sometimes that are very long running for machine learning or data analytics. Those can have quite a few demands on memory and CPU. So this is a different kind of workload than someone just working through a shopping cart. And so just to give you this illustration, our projection, you'll notice in January we tend to have an uptick. Our projected spend for January on the right of this was going to be over $30,000 for 1 month. And you'll see that it has significantly dropped off, and that is when we cut over to our bare metal. That was our Google Cloud spend on a monthly basis going back a few years. So you could see a steady trajectory of growth, and the drop off on the right side was when we switched over to the bare metal. So I want to talk about how this all started, how this began, why we ended up in GKE, and why we ended up with certain tooling that we did. And like many things, this didn't start like where we had all the tooling and processes and in target in mind. It happened a lot more messy and organically, as things tend to do. It was kind of a collaboration between the IT for the college and another department, the Department of Statistics and Applied Probability, PSTAT. We still have a lot of shared branding with them for our open source stuff. And they initially tried Docker Swarm, and it needed a better scale. And quite frankly, Jupyter Hub just really needs to run in Kubernetes. The real reason for Google Cloud, we did try AWS, but frankly, the documentation at the time was written for Google Cloud. That's not a small thing, right? If the documentation gives you a pretty well step-by-step to getting started, and you have to translate that to another vendor's way of doing things, that could be a lot of overhead, especially when you're just trying to get the proof of concept off the ground. And we also had quite a few free credits. So we had free credits to spend, you might as well try them. And so as that was going on, the word of mouth, we started to get more adoption. Now we have users depending on this. We're now in production. So that's how we ended up on Google Cloud. And this is a good thing, right? If you don't know what you need for hardware, you don't know what your scope is going to be, you don't already have Kubernetes in-house, public cloud is a great way to get launched and get started, right? This is all a good natural thing, a good natural starting point for this. And part of that was the Zero to Jupyter Hub project, which is now rebranded as Z2JH, which I don't think is more memorable. But this came out of UC Berkeley. It was the other UC. You might have heard of them. They did some Unix distribution. But so UC has a long history in open source, and I feel like our Jupyter Hub stuff is continuing on in that wonderful tradition. And so UC Berkeley, and there were other UCs involved along the way, but they produced this Zero to Jupyter Hub. And at the time it was a, hey, you need to get started in Jupyter Hub, you don't know where to begin, here's how you could get up and running on Google Cloud right now. And it was Helm-based, which is a great way to manage your application deployments on Kubernetes. I'm saying that following up on an Argo talk, they're great too. But this is there were also some useful built-in things specifically for running on public cloud, right? You have horizontal scaling, and part of how you achieve the cost savings is by bin packing, but you have hot spares, so hopefully when your users are logging in and making more demands, you have instances ready, but start scaling up another node before the users need it, hopefully. If you've sized everything and optimized it right, hopefully the users won't know that there wasn't enough resources, but by the time they log in, it's there for them. And you also have culling on the other side. So when users aren't active for a certain amount of time, we shut down those instances, and then we can kill off nodes. So that also saves on our spend. So it's on-demand spending. So those are all wonderful tools that are built into the concept of this Zero to Jupyter Hub Helm project for it. And the tooling was initially built on Docker Hub. We had a public team-level subscription, so we were paying for that. It was based on GitHub Actions for the deployments, and kind of like loosely, not consistently, maybe everywhere for some other things. Terraform Cloud was interesting here. We used Terraform, but the reason for Terraform Cloud was that they didn't have a good place to save the state file. And that's a very important thing if you're doing Terraform. So if you have to do any follow-up after your deployment, it's based on that state file persisting. So it was kind of funny that we were spending money for Terraform Cloud, but GitHub Actions is actually doing most of the work, but we were paying money just to store that state file for each of the environments. We're using GitCrypt. Just as a spoiler, don't use GitCrypt. And that's nothing about, yeah, we'll get into that. Some of you might have already had some relatable experiences. But faculty and researchers also were curating their own images with support from IT. Again, this is, we needed a starting place, and so we had some faculty that knew enough that they could create their own images, and others were like, hey, can you help us get started with this? But it was largely on the faculty or the research people to maintain their own images. And each classroom was its own separate Google project, its own Kubernetes cluster, and had its own DNS subdomain. So every classroom was entirely distinct in the Google world, which is kind of great if you don't have like an otherwise way to be multi-tenant to keep everything separated. We're just using Google authentication since we already have Google for our org. Now, I have a tooling stack. Let's hear about the tooling problems. Right? There's always these ups and downsides. So one of the big problems is there were a lot of manual steps for each deployment because we were creating a new Google project for each deployment. So you had to create the project, you had to set up the billing, you had to enable GK, you had to set up the OAuth for it and generate your tokens and stuff that you could then also, with the right permissions to feed Terraform later so that Terraform could create the cluster and everything. There was a lot going on. We had to create the Terraform project. There were a lot of manual steps for what should have been an automated GitOps process. So these deployments could take, at the time, could take an hour before you got done with all that and your wrist hurt from all the clicking around in various UIs. There was a lot more manual stuff than there should have been. Gitcrypt was a problem because sometimes you think that it's encrypted and it's all working, but then you push, and now your credentials are in GitHub, and now you got to revoke them, and that's not a fun time for anyone. That's never a situation you want to find yourself in. So just a general suggestion. This isn't so much about Gitcrypt as much as a general suggestion that you do not store your credentials in a GitHub repo. Just don't do that. Terraform was a love-hate relationship. The constant having to keep the dependencies up to date. So you make your deployment, or you go to update it, and you find out that the Google plugin needs to be updated, but that needs to be updated with the Kubernetes plugin, which needs to also be compatible with another. So there was a regular kind of whack-a-mole. Hey, I need to make this update, but now I've got to pause that while I fight some dependencies in the repo for a little bit. That was a regular pain point. Also, we'd sometimes need to go in and just, hey, we need to make a quick update to the Helm chart to fix a problem right now in a classroom environment. And instead of just patching the Helm, it said, oh, we should be updating Kubernetes. So now it's doing a whole rollout of all the nodes before it gets around to patching the Helm. And it might have timed out. And so my quick, simple patch wasn't so quick and simple. And if you try to go in and just manually fix it, well, now you run the risk of that environment no longer being in sync with your state file, and Terraform will no longer talk to it anymore. That's not a fun place to be. And sometimes it broke for no good reason. And we never figured out why, but we would retry the same job and it would work. It wasn't very good at idempotency for us. And also, we had this really interesting problem with a race condition of some sorts, because we were deploying on Google Cloud, but we had our DNS, we were bringing our own DNS. So when you're deploying Google Cloud, we would have Terraform spit out the IP at the end when it's already up. But I need the IP to make the DNS entry. So then I have to go and put in the DNS entry. By then, Let's Encrypt has already given up. So now I have to figure out how to restart that pod so that it could try again, because the DNS entry didn't exist until we'd already deployed it. This was not a fun problem. And then we entered in this new era in that within a short amount of time, the devs that built this whole first iteration all left the organization. So I don't know if this is a relatable experience to you, where you've suddenly inherited something of someone else that's not simple. But this is what happened. And by the way, this isn't all bad, right? Because this is, even though we had all these issues, this is still like, we had documentation. It's in Git. This wasn't dependent on someone's muscle memory about where to click on Google or what not to do all this. We had pretty good documentation and a place to work from because of how much of this was in Git and how much of this was already documented. So it was a difficult situation, but it wasn't impossible. And that's a very good thing. But while we were just trying to keep the ship afloat, we were still popular and continuing to grow. So we were just trying to keep courses up and going, but people were still demanding more. And so we discovered more and more pain points to this. So image curation, I mentioned that faculty and researchers were largely left to their own to curate their images. Well, some faculty, I'm not going to name names, but don't really like to update their syllabus that often. Or they already have a very particular version of something that works, and well, you know, we're just going to keep that for 4 years. So that is not great for your security, for an internet-facing service to not have patches in your images. Just because it's in a container does not mean it's secure. On top of this, some of the images could no longer be built because the dependencies were too old. So you'd have a case where a professor would say, hey, I want to use that same image I've been using for years, but I need to add this one Python library. But now I can't build that image because the dependencies are broke. And some of these images took over an hour on a Ryzen 7 laptop, which means that that simple request could take days. That's not fun for anyone. The professor wants their image, and I've turned my laptop into a space heater. This is fine. Enter Jenkins. This isn't the last time you're going to see Jenkins here. So one of the things we did was we looked at all the, we had a lot of common things among various images, right? We had a lot of the images had some similar tooling that was just kind of guaranteed that this is going to be added on from something. So we grouped those together, and we based off of the upstream Jupyter images because they were really well maintained. But we had our own institutional, very common needs and tool sets across the board. So we made base images, and we leveraged Jenkins to do that. So we had a base notebook and a base RStudio one. And so whether or not they're using our notebook or RStudio, we just go ahead and package both, and they can use whichever one they want. And we eventually added SciPy and PyTorch, and we have ARM images and some that support CUDA. But we took over the image curation from the faculty. And I don't know if you've ever tried to get faculty from various departments to agree on something, but I expected a lot. I expected a fight that never happened. It turned out the faculty were largely really happy for that part of the responsibility to go away. And so that was a very pleasant surprise, because now we have something that's up to date, and the faculty don't have to wade through the dependency mess or have to wait days to get an image that may or may not work. So we also added tests, and we would rebuilt them and tested them and would update them at least weekly. And so all the courses were downstream images on those bases. So if we ever update the base image, all the downstream images automatically get rebuilt with Jenkins. And so the SciPy and the PyTorch and the base images, they can all share the same repo source, and Jenkins will just, the Blue Ocean build for that looks ridiculous, but it's kind of amazing. It's doing all this parallel at once, and we have the workers in Kubernetes now. So it's a glorious factory of images always being tested and deployed continuously. And it really added a lot of sanity to the chaos. And it let us focus our energy more on things that were serving our client base better. Other improvements, we were trying to make Google Cloud work well. So when COVID-19, when we were, everyone was remote, when people came back on-prem, now most of our users are, this is kind of the opposite problem that you usually have in the DevOps world. Usually you're trying to geolocate and make sure you have service in Europe and the United States and China, all similar. But now we have kind of the opposite problem. Our users were all spread out, and now they're in one location. And that's when the latency became way more noticeable, because I can no longer blame it on your home network. You know, if you're having latency problems and timeouts, well, that's because we're talking to Ohio when we should be talking to Los Angeles. And so moving stuff closer and picking regions that were closer helped with the latency. And we also picked different instance types. Moving from Intel to the Epic N2D nodes saved money, and we got a little bit better performance out of it. We had more scripting of the deployment process, and we did some more automation around the cleanup of storage that had been behind in the SLAs. That was a very manual process before, which means it wasn't getting done on a regular, timely basis, which means we were spending money that we didn't need to spend. So automating the storage cleanup to our SLA lifecycle helped with that. And that essentially cut our GCP bill in half. That's great, except we kept getting more popular. And we also hired another Kubernetes engineer to help with that, he's over there. So this is a good problem to have, right? Because our service is growing, because it's working for our user base. We've connected with our user base. We haven't done a lot of marketing, so it's users telling other users, hey, this stuff really worked for our classroom and for our research, and so have you considered using it too? This is a very organic, word-of-mouth way to grow. And this is good. This means that you're doing something right here. However, our costs continue to skyrocket, and so we got to a situation where it was too expensive to justify affording it, but it was too important to kill. And so that's what led us to this interesting place, because we were projected to spend over $30,000 a month. on GKE. Now, if you've done bare metal before, you know you could buy a lot of hardware for $30,000 a month. So it seemed obvious that we could make that math work out. So that led to the path to on-prem. The migration took about a year. And during that time, there was a lot going on, right? We had to provision new hardware. That means sourcing your vendors, figuring out what we were going to do. We essentially took the same what we were running in N2D, the N2D sizes in Google already, and essentially bought that same hardware, more or less, and had it on-prem. So that's less surprises, right? We already know it's going to work on those Epic nodes, so let's just buy those Epic nodes. And this also gave us an opportunity to retool our workflows. This was also to address pain points, but also there's different things you have to manage, whether or not you're public cloud or on-prem. So you have some different trade-offs about your responsibilities and what you are going to take ownership of and manage between those two worlds. And we evaluate many commercial vendors because we're doing this in production. Even though we're running on bare metal, we're still went to pay for commercial support. That's the responsible thing to do. And so we evaluated a bunch of them. The top three were Sidera Metal, which is Talos Linux, Red Hat OpenShift, and Rancher. And I would say if you're wanting to consider bare metal, these are all vendors that are here. You should go and talk to them. I'm not going to tell them that one is the right one for everyone. We ended up picking Rancher. The SUSE one was the right one for us. But definitely, if you want to do bare metal, talk to these vendors while they're here. And so this gives us opportunity to address some of the pain points. We didn't have great logging and monitoring. The secrets, our deployments were cumbersome, our GitOps could have been better, and we could have had better lifecycle management in line with our SLAs. Like our Google cleanup still depended on someone remembering to run that script on a weekly basis or something, right? It'd be nice if that could be automated too. And we also have some new challenges of we now have to install and maintain an operating system. We didn't have to do that before in GKE. That's one of the things that it abstracts from you, right? It's running this black box container operating system that you don't have to think about too much, right? And now we have to think about how we're doing networking and how are we going to do storage. So the bare metal processes for us are now more cloud native than when we were running on public cloud. And that's because we're doing better workflows and better attention to our tooling and processes. So the secrets management, no more Git crypt. And I don't mean this as offense to anyone that is maintaining Git crypt, but that went away for us. We had tried HashiCorp Vault, and we just couldn't really get people to use it. And then they HashiCorp relicensed, and that gave us a great excuse to do something else. So we checked out a bunch of them and went with InPhysical. We could self-host it ourselves in our own Kubernetes, and it had commercial support, and it integrated well with Jenkins and Ansible. And one of the things I really love about it, it had a built-in concept of your credentials having a dev, test, production workflow to them. So you could have distinct credentials and different configs for those environments as a built-in, out-of-the-box thing with them. This is a wonderful thing. I will note that this is open core. Most everything else I'm going to talk about is fully open source, but I feel obligated to point out that this one is open core. They have been great to work with, and they've accepted pull requests and whatnot, but that's the thing. Logging before was a real problem, okay? So our logging was largely going into kubectl to the specific environment and trying to look through the logs. And so that often didn't happen right as events were occurring. So you come in on Monday and a faculty user says, hey, Friday evening, someone reported this problem. They can't remember who it was, but someone had this problem. Okay, that's a needle in a haystack issue. That's a big time sink of spending your time going through a lot of logs. You could have hundreds of users in a course to try to find that problem, and you might never find it. And so this is one of the things that we're able to do now in our new stack is we have FluentD, FluentBit capturing all the logs for Jupyter environments in Kubernetes, putting them in OpenSearch, and that means that I can now look for specific errors for a specific environment within a certain time scope. So if you give me someone had an error in this class around this time, I now have a really good chance of finding exactly what's going on. Because it could just be that the user's Python was not the best quality. That happens. But now I have data to back that up. That's important. Monitoring. So we're using the Prometheus Grafana Alert Manager. If you're doing Kubernetes, this is probably a familiar stack to you. And so Alert Manager is really great because if there's a problem, we could get a Slack notification, you could shoot an email. It helps us know about it before. Hopefully the users say, hey, our stuff is broken. Hopefully we now have a chance of knowing that. The Grafana brought up an interesting thing because we found out that on GKE our pod limits were a lie. So if you've done Kubernetes, you can have a request and a limits, right? Requests are what you're guaranteed, and limits are what if it's CPU, it'll compress. If it's memory, it might add a memory kill at that point. And this is the completely fair scheduler in Linux. Turns out to not be completely fair everywhere. It's more fair than others, depending on your Linux distribution. And so what we thought were sane limits that we've been running in Google Kubernetes all along, it turns out that Google, the operating system for Google was just kind of like quietly ignoring the limits and would just let stuff run where it otherwise probably should have been killed if it were really taking you at your word. And we found that out because of Grafana. Users were saying, hey, this stuff is really slow. And I thought, that doesn't make any sense. We've got, a million cores in this cluster. But I could go into Grafana and see, oh, they're getting throttled because they're hitting their CPU limits. And I have data to back that up now, and it's not just anecdotal someone's experience. So we found out we need to adjust our limits going to bare metal on a different Linux distribution. The deployments. Jenkins is back. No more Terraform. I was not sad. We're using Terraform for other things, but we have Git template repos in 4JO. So when we want to make a new deployment, we create a new Git repo that's built off of a template in 4JO, which is a self-hosted Git that's sponsored by Codeberg. It's fully open source. It's awesome. Fedora is adopting it as well. And so any updates to that just automatically trigger a Jenkins pipeline. So if I need to patch a course, I just edit in the Git repo, and Jenkins does the rest. And we have a PR-driven dev test production workflow, so we can now test the changes before we roll them out, which is something we weren't easily able to do before. And we could do that at the image level, but now we can do that at the whole Jupyter level, which is awesome. And we can approve PRs based on what we can actually not just assume, hey, that looks good, but now we can actually log in and try that. It's Hellman and physical driven, so we have a way that the environment credentials are just specific to that stage, and the workers go away because they're in Kubernetes when they're at the end. And we also have better testing now. We can automatically roll back. If we get all the way to production and it crashes, it'll automatically trigger a Helm rollback through Jenkins, which is awesome. And that has saved us more than once. And so these are wonderful. If for whatever reason, we don't have to as often anymore, but if for some reason we had to do a manual patch of environment, we don't have to worry about breaking a state file. So I hope that this, now that I've explained all that this isn't going to be too overwhelming, but this is what happens when a faculty member or researcher requests an environment. Because they'll tell us, hey, we need an environment for this term, these many users, and we need these kinds of things in our base image, right? And then they hand it off to us. We get a ticket in Zendesk. And so there's kind of two things that happen. We have, on the top, you see what happens at the image level. We take our base image, and then we add any other dependencies they need on top of that. And then Jenkins will just automatically create that, test it, and send it to Docker Hub. So then we will just continue maintaining that image and until it's no longer being used. But Jenkins will just weekly continue to test and rebuild that image so that when upstream dependencies change in Python and break something, hopefully we know about it before we need that image to build again. And on the bottom side, we see the deployment itself. So we take our Git template that has our Helm templates and whatnot. That goes into 4JO on-prem. Jenkins picks that up, merges that, and sends it to Helm and tests it and deploys it. And then off to the side, users can also bring in their own data through ForJO as well, or GitHub or whatever Git they want. So if you're an instructor and you want to bring in your own notebooks, your own course materials, you can curate that yourself, and it'll be there waiting for your users as soon as they log in. It's called NB Git Puller. And so that is built into all of our images as well. So the bare metal stack itself, my nick online is VW Bus Guy, so you knew an image was coming like this. This is a beautiful Carmen Gia. It's a beautiful bare metal stack. Anyway, we now have new things to take care of. We have the operating system, we have common service automations, we have networking, and we have storage. These are all things that you consider differently now than when we were on public cloud. So the operating system is Element distribution based off of SCaLE Micro, which is SUSE Linux. But this is specifically geared toward Kubernetes. And so you define your customizations with some cloud data, and it's all customizable with YAML to some extent. But this is the short of it is you have some YAML that helps define any customization. So if you need to include like the Ceph module or something like that, or set up some LVM or whatnot, you can bake that into the image if you need to customize the operating system. And it generates an ISO that you would initially boot via BMC or some Pixieman or something like that, that's going to call home. And this is probably a familiar story if you've done OpenShift as well. They have a similar deployment method. But Elemental can also roll out upgrades for you. So it'll do a rolling reboot of your servers, and hooray, you're on the newer version of SCaLE Micro. It can also create standby nodes that you can tell it these are okay to go to these clusters or for these roles. And so if you have a node that's misbehaving, Elemental will reboot it, wipe it, and in the meantime bring some other node that's in standby. So you have a way to roll in and out nodes from your bare metal infrastructure that way. Fleet is a similar concept to Argo CD. This is kind of Rancher's concept of fleet. I guess maybe a key difference is it still actually uses Helm. But you can write a fleet in such a way that it'll automatically apply to any of the Kubernetes clusters in that stack. So if I create a new Rancher cluster, it'll go in our stack, it'll automatically install Cert Manager and set it up so that our ingresses will automatically work with Let's Encrypt. And so that's just a nice quality of life thing. If I just want to get up and started with a new Kubernetes environment, Let's Encrypt is just going to work out of box, which is awesome. Networking, this is there are different considerations, right? If we're in public cloud, right, that's not attached to our campus network. That's out there somewhere else that we're pointing to, and all of those Kubernetes environments were distinct. Now we have to figure out how to have secure networking in our own house. You know, that's a very different thing that you have to think very intentionally about. And I'm gonna, as I go through this, I want to know if you notice any themes for this slide. So we have an internal DHCP NAT VLAN situation. So they can get out, but they can't publicly listen directly. They have to go through HA proxy. Which is the next part here, the HA proxy and keep alive D that explicitly does the forwarding the front end for that. So the configs that are defined in Git, and Ansible AWX ensures that the server configs match Git declarations. And our DNS for that also is the configs are defined in Git, and Ansible AWX ensures that the server configs match Git declarations. And so for all these three things, the configs are defined in Git, and Ansible AWX ensures that server configs match Git declarations. Do you see where I'm going with this? So they're defined in Git, and Ansible's doing all the automation for us, and this is way easier than what we were doing before. We no longer have that race condition of, well, we don't have the IP until it's deployed, and so Let's Encrypt has already failed, and now we have to do something manual over here to come back. We have a lot better sanity with this. And WireGuard is also being used on the back end. So the nodes actually are talking over WireGuard. Even though this is in its own VLAN and it's NATed, the communication on the back channel between the Kubernetes nodes is also encrypted with WireGuard in our stacks. The storage, this is kind of fascinating. So we have two different ones. Longhorn is the SUSE one. It recently got branded to SUSE Storage, I think. but it's open source, and you do not have to be on Rancher to run Longhorn, right?
And give you visibility in order to know what is going on in the cloud right now. So that's what we see. We see the client pod, which we have there, the Envoy sidecar, for example, one of the implementations of the Serve Mesh. And in the service, we also have the Envoy as a sidecar. And in this generic flow, we have also a software load balancer and Istio gateways on the way. So why not using our Istio gateways and Istio metrics in order to see where is the latencies goes, right? So is it reflecting correctly? That's the question. And that's what we were facing at eBay during incidents. And what we learned that this is one of the main challenges. Is it reflecting correctly? And can we detect and mitigate the incidents very quickly? Because if we don't, so customers are having a bad experience, and bad experience equal losing money, basically. So another thing is in the challenges that a component cannot really measure itself correctly, reliably. So this is a very tricky to do, because we have all the stack of different layers inside of each of our services, and the latency can reside in the kernels, in the kernel layer, and also on different applications layers within the same service. So it is a question how to measure yourself reliably. And the main goal when we want to know where in the process the latency is to spot and detect those incidents efficiently, to be sensitive about it. And if we detect that we have incident of latency during that process, we want to pinpoint where in order to mitigate it efficiently, because we have a live incident that is causing us problems. And that's actually quite of a challenge to do so, and we will see it in the next slides. And basically, if our clients are indicating some latency, right, it is not necessarily indicates anything that is network related. It's not saying anything also on the service side. You don't know where the latency, it could be DNS, it could be a lot of other things. So we are focusing really here in the scope of our problem definition, problem statement, in the east-west communication within our data centers. And we want to early detect those issues and mitigate them. And as I said before, regarding is your reflecting, metrics reflecting correctly what we are seeing. So Istio metrics basically are sampled, and when you sample your traffic, so it not necessarily indicates and not sensitive enough to show you different various patterns of latencies that are building up in your network. And so you want to achieve a visibility of your real traffic and be sensitive about it. And so what we want to achieve is a latency breakdown where we can pinpoint all the latencies that we have in each of the points. So for example, I want to see in each of the arrows what is the latency between those two arrows, right? So coming back to the analogy of the kitchen, I want to see if the oven is performing well enough, for example, to know if the anomaly of the latency is residing in the oven, for example, or in the Istio gateway or the load balancer. So this is our main motivation here. We want to basically have a latency breakdown that will be with the granularity and the resolution that we need for early detection. And after we can early detect, the latency breakdown can help us to spot specifically where the latency resides. So how can we address this issue and know what approaches can be done in our mesh? So using our mesh is basically what we are going to do. And we have a mesh in our modern cloud. And the mesh is offering us a lot of features. And we want to leverage the features in order to have those breakdowns that we need. So the key concept here is basically using the Envoy HTTP filter to measure different latencies across the flow. So for example, on the left diagram, we have there the Envoy in the center, and we have the downstream and the upstream, because this could be anywhere in the flow, right? And we can see basically a traffic comes in, one of the requests, and we have the horizontal red lines that represent the latency in between. So you see that the request is coming in, and then we have a latency of the Envoy itself. And then the Envoy proceeds to moving forward the messages. So then we have the server latency, and then the response come back to the client or to the downstream, basically. So this line can be represented in the Envoy perspective in the different colors of lines represented by different latencies measured. So we want to leverage that measurements into a measurement that we want to use them afterwards. So let's look at it on unfold diagram. So the clients that you see on the left side is the same client on the right side. So when the request is passing to the server, we have the response from the server, and then it passed back to the client. Keep in mind, notice that the load balancer, for example, is not in the response way back. So it is not necessarily, might be symmetrical, but it really depends on your architecture. And the idea is based on really injecting those measurements that we do with the Envoy during the flow. So for example, when you pass the EC2 gateway, so we start measuring the time that we see in here, right? So we have the time for the upstream, so it starts measuring. It will end measuring the time until the response comes back. And when we inject this measurement of the latency into the HTTP header along the flow of the response. So we have the request. The request can also stack injections, but the response accumulate all the measurements that are done with the Envoy until it reached back to the client. So what we have here is from the request to response, the response having in the HTTP header all the measurements, different measurements that we have accumulated during the flow. So now what can we do? So let's look at it like this. We have those components that we've seen previous slide next to each other. And the red lines representing the latency that each component has. So for example, there is the server latency, the upstream duration, which is measured by the Envoy sidecar. So this Envoy sidecar is of the service itself. We have the gateway duration, which is the measurement of the Envoy of the EC2 gateway. And we have the overall client duration that is perceived by the client. So what can we do in all those measurements? So we have those measurements injected to our HTTP header. And then, by subtracting the values, we can definitely isolate different latencies that are interesting us during the flow. So for example, one thing that is interesting us is the mesh latency. We want to see that latency to be around the average that we are expecting. So it's not dependent, the server duration is not part of this mesh latency, right? The server can serve in seconds, but the mesh latency must remain the same, must remain with the same performance. Also, we can isolate the gateway latency by subtracting the gateway duration from the upstream duration. So it will give us the pure EC2 gateway latency. So all those be done with those measurements. But where basically we are doing all this magic. So this magic happens in the client. And also, by the way, the Envoy can measure the server itself. So it solves us the self-latency of the server, or self-measurement. So basically, in the client, we have we implemented different dependencies across different platforms. So we need a good coverage in order to get all our real traffic. We need to implement for different clients within our application, right? We have services that have clients to call different other services. So we need those dependencies to catch requests from different clients, and we also need to be with a good coverage with our different platforms in our cloud. So we want this coverage to be on the major of our workloads in order for the data to be very sufficient to early detect incidents. And the key on this one is to have a low overhead over the performance, right? We don't want to harm the performance of our network. So the Envoy, basically the features are not giving us any overhead that is significant, so the performance is quite good. And also, we need to pay attention when we implement those dependencies on our clients that it will not be a significant impact. And it should be very well written because everything basically gonna happen if you are not writing it right. So what we have on to this point, so we have a coverage of dependencies. We are injecting the measurements across our mesh network. And so how can we achieve a better results? So we need to fit our histograms basically to represent the data that we are looking for. So if we are measuring the mesh latency, for example, we want the buckets to be distributed according to the distribution of the mesh latency. So we know what is the mesh latency performance. So that's how we know how to fit our buckets to represent what we are expecting from the mesh performance. For example, mesh network cannot exceed a huge numbers, right? It is a network. It cannot hold a lot of information, so it should be somewhere around 5 milliseconds to 500 milliseconds. So we know how to distribute the buckets correctly. And when distributing this bucket correctly, it gives us the high resolution we need to early detect those incidents, those latency incidents. So it is crucial to fit your buckets according to the latencies that is measured. So after we have the data, which is collected by different collectors, we want to, on top of it, have some different aspects of the data. So basically, we want alerts, right? If we have some incidents, we want the alert to be actionable. So we need to add different labels during our collection. And those labels can be cause significant amount of data to be produced. So we need to calculate our cardinality in order to really not exploding the data. So we are collecting a lot of data, and it's very important not to over labeling our data. And we can also, because of the huge data, we can construct recording rules, a very sophisticated way to visible the things in order to see what are the latencies that we are getting from the mesh network and from our tools and our CA tools. So if we have some anomalies, we can have alerts also, depending on what we are looking at. So in this case, we are looking on the gateway latencies, and we can see down below that we have different gateways that are having very huge spikes of latency. So with the different labels and with the metrics, we can also have a tools of root cause analysis that can give us a clue where our incident resides and where the latency and what causing the latency, and that's how we can mitigate the incidents very efficiently. So that's part of it. So we want to be sensitive enough to know when we have latencies deviations, and we want to know where the root cause of it right often. And different percentiles should be applied in this case. So it could be when it is huge incidents, so we might look on the average, but when we have a very flow related issues, so we might see it as something that is 99%, for example. So we see on the right the different alerts that we get during the alerts. So when it comes to triaging, we in the middle of investigation, basically, of where our issues are and where the latency is. And it might be also in the downstream dependencies, and also, so you might not see that a specific pod is having an issue, but you will see it in the upstream pods. So basically, the open telemetry gives you the whole span of the transaction of what you are doing. So you basically can see different latencies across the transaction. And those latencies that are interesting us can be injected as spans into the open telemetry. So during our triage, we can also use it in order to see, oh, we have latency in that part. That's explain our overall latency in the start of the chain. So this one is very good into triaging, because in triaging, we're not looking into specific thing, we are looking at a chain of events. And so this one is very strong feature. And we also can bring more attributes into those spans in order to understand a lot of different things. So spans must be continuous, but if we have latencies that are not continuous but happens in different parts of the chain, so we can basically have the attribute to accumulate the all latencies. So it's really help us when we can't see it visibly, we can look at the attributes and also have some value from it. Okay, so the real world practice basically. So we can have a very nice visibility using those measurements and those breakdowns. The breakdowns allow us to see in each of the points where we've seen the probes before, what is the latency. So side-by-side latency is a very useful way to visibly see it. We can see all the lines from the service to the client and between. So the in-between, if you see the lines, if we have some issue, and we will see it in the next slide, we can see very easily latency deviations. And also the breakdown can give us the latency for each of the components on the way, which is very useful when you're looking on some incident and you want to see, okay, what is going on? So you might see a spike on a different parts of the breakdown. So a sample incident that we had at eBay. So we definitely see here a huge spike, and we can see differently that it is something that is related to the Istio gateway. And when we look at the gateway's latency from our metrics, we can spot very fast where the gateways that are having the huge latency. And those latencies are coming from our real world traffic, right? The metrics are representing our real traffic. and it is very useful. And all this data is coming from our workload. So this is a very efficient way to spot those latencies. And we know the gateways, so we might look at them also. And here is more view of the mesh. So we call it isolated latency because it is not continuous, and we can also measure on the time from the start when we are passing the gateway and in the end when we are passing the gateway again. And we can also see markdowns that are issued from the software load balancer during that incident. So it is very useful when it comes to root cause analysis, etc. So upon these metrics, we can also define some goal for our mesh network latency, right? So we want to serve, for example, 90% of the request under 20 milliseconds. So we get some percentage of how we are doing with this definition, right? So as we can see in this SCaLE, that during the incidents, our performance is dipping. And the actual detection time was in 6:35, for example. This is real data. And with our anomaly detection and other tools, the potential anomaly detection time could be 2:30. So this is about 4 hours of having an incident, maybe not in the most disaster way when we have after the actual detection time, right? So this is something that is degrading. So we can catch the degradation at the starting and not during the worst case scenario. So this time, these 4 hours are very crucial in order to mitigate the issues and to understand what is going on. And those metrics that comes from the real traffic can give us really insights and give us the ability to early detect those incidents. So how SLO dashboard look like? So we can tune it actually for all goals for each of our different components. So if we're looking on the mesh network, we can define some goal, and if we are looking also solo on the software load balancer, we can define different goals. So those goals are monitored, and when we have some spikes that consume a lot of burn rate of errors, we can definitely initiate an alert for them and know how our network is doing. Okay, so wrap it up. So we have the metrics basically coming from our real workload. And this is very crucial when we want to know if our problem is from the infrastructure or from our services, right? So part of the incidents are from our services, and we can see it very clearly in the latency of the services. But when the services are telling us that everything is all right, so then questions might come up, and you say, okay, where are our latency? So when you use real traffic metrics, we can quite easily get the root cause if it's in the infrastructure or not. So this distinguish is very important in order to know where to look from. And the second thing, basically, is we want to shorten the time to detect and mitigate and during network issues. And it is very crucial to have a visibility of your latency and to have this breakdown that we have talked about in order to know really what is going on. So without it, you're really blind of what is the process and where your latency resides. And basically, the reflection of the metrics that is come from real traffic and the injected measurements from the envoy, what we've seen, is really good in order to have the shorten our mitigation detection. And another thing that we talked about during the covered slide, we want these dependencies to be in the major part of our workload. It means that we need to implement it for different platforms, and it gives us a shared baseline for all of our workloads to have this ability and to enjoy the feature of knowing where the latency is in your flow between your client to the service, basically, and back. And the first thing that is very important is to use all what we've seen here for triaging, for alerting, for anomaly detecting. All the pillars that we are using are very crucial when you want to pinpoint if it is a network issue or not. Okay, so thank you for listening. And if anyone has some questions, you are welcome. Thank you.
So, questions? Anyone? Going once, going twice?
Sold.
Okay, well, thank you very much.
Thank you.
Turning on.
Okay.
I will present and.
Yeah. Okay. Okay. Well, you have an audience, and it is time.
We have audience.
Yep.
And then you can choose and be like, oh, this one was
Yep. We're going to start now. So, welcome everybody to an excellent talk about using KubeVirt. How many of you have used KubeVirt before? Yeah. Okay. Wow. Cool. So you're gonna learn a lot. Our speaker today is Fabrizio Segura from Veritas, who's joining us all the way from Colombia. Yeah. In order to teach you about migrating to KubeVirt. So welcome.
Thank you. How can I power on this? Can you hear me? Yeah? I see yes. Also at the end. Welcome everyone. The mirroring is not working, so I will be looking what you see. What you see is what you get, what I get. So here we start. We will talk today about virtualization on Kubernetes. It's a topic that it's out there since a lot of time. Probably you have heard that it can be done. Today we will see how we can done. And special gift will be a repository with a Terraform provider, KubeVirt, that you can run basically on your home computer, the same thing that you are going to see. So let's start here. Let's see if I can move the presentation, or I will have to do something like, because again, I'm not having the mirroring working, and the space is either working. So we will do a presentation that is just manual. It was the same the last year. This is the beginning, breaking free from a legacy virtualization. This should work now. Let's see. Yeah. Agenda. So we will start with a brief introduction. Virtualization systems are out there since the 60s. You maybe will say, no, impossible. I know that VMware started in the 90s. We will see why it's not that way. Then the challenges. Everyone here could imagine that there are challenges these days with traditional virtualization. And KubeVirt, this guy that we are going to see how it works today, the benefits of a migration if you are using the cloud, if you are using that on your machines, what will be the use cases, a demo that everyone will like a lot, example of companies. There are just two examples of what they did to get out and step out from the legacy virtualization, and finally, you will have your space to ask whatever question you want. The questions can also be driven offline, so you just grab my QR code, it's LinkedIn profile, I'm that man, younger because the photo is 10 years ago, probably. The suit is still that one, who met me 2 days ago in a meeting that we had. I was still wearing that because I'm out of money and I don't buy a new suit. And I'm Fabrizio Segura, a QB astronaut and chief engineer at Veritas Automata, the company where we do a lot of things like these. We are exciting, committed to do trust in automation and everything related to cloud, edge, supply chain, a lot of things that you will enjoy just looking at my profile. So in introduction, as I was telling you, these slides will be available in the repository that we have on GitHub for everyone, so you will be able to follow up and read the contents. Probably there will be an extended version there. We talk about the history here. So IBM started to do a specific set of activities in the 60s, already creating a sort of virtualization of processes. That was something that if you are using Unix since a lot of time, you already know that there were CH root environments that could be considered like our containerization of today for the Docker initial approach. But there was something that they did in the 60s, virtualizing part of the hardware. And if you are an expert on Power Series or whatever IBM is doing in these days, they have logical partitioning on hardware that is real virtualization, but the way that is running on top of a real hardware. And then we know that in the 90s, VMware started to be available as executable on Windows, Windows Server, the VMware server on top of Windows, or on Linux, whatever they were, server, then workstation. There was something that was really available in that time, and at the beginning of 2000, it was consolidated as something available for people. So 1998, more or less, it was when they started to do this kind of abstraction. And the difference in innovation was that you could have been having your own kernel for Windows NT or for Linux running on top of a workspace that was really a virtual workspace for virtualization and running these kind of technologies. Now here we have the elapsed time. That is more or less the summary of what I said. We see 98, 99 VMware. Then I considered putting a special mention for Xen, because if you have been working with AWS in 2012 or when they started being more productive in 2015, you probably noted at that time that the kernel of the virtual machines, the EC2 instances, was having a Xen reference. That was a way of virtualizing and emulating the systems, abstracting the kernels in various kernel image disks that in AWS were called AKI, Amazon Kernel Image. And you would have been able to put your own kernel on top of that with a lot of problems, and that was how Xen worked. Then they migrated to KVM, that is the special guest of today, because KubeVirt is using KVM, so if you think to run KubeVirt on your Mac, it will not be possible. Sorry for the Apple guys, but you will have to buy a machine that is able to run Linux, because the KVM virtualization is coming from that point. You could do nested virtualization with VirtualBox on top of a Mac, but nested virtualization is very costly. So I suggest that eventually you do something on a laptop running whatever Linux distribution that you want, and following and finishing with the elapsed time in 2018, we had KubeVirt that has been evolving the world of virtualization, especially on top of bare metal. So if you plan to try on a smaller system, there are very available how-tos to run it on Minikube, to run it on smaller solution. Also on Killer Coda, you can run a sort of emulation of KubeVirt, but I suggest you do that on real hardware because it will be problematic otherwise. So what I see a potential future option that is really available in terms of market for some companies that are already abstracting the two kind of offer that we can have is that legacy virtualization. Here the icon is for OpenStack, but you can consider whatever kind of VMware, VirtualBox, or emulation and virtualization that we have can be combined with cloud-native virtualization. So running a Kubernetes cluster on the cloud, you have two realities that are always expressed with running containers on top of the two things, and reaching the combination of these two technologies will give you the ability to run mixed workloads. That is basically, you don't bother about service discovery for your virtual machines because you expose a service like you do for Kubernetes. Raise the hand if you know the services on Kubernetes and how they work. Okay, there is some presence. I will show you in the real demo how a service on top of a Kubernetes orchestration context can be exposed by a command line, just a kubectl expose with a port and something like the reference of a service. This is a big advantage for the third hexagon that we have there, that is expressing how you can control the port available for an SSH server, just exposing it on top of a running pod or a service that is inside Kubernetes. Here we have the pain points of legacy systems, how we have always experienced a limited automation because you run the virtual machine, but it's hard to have a life cycle. You will need to use several additional tools for maintaining the effective availability. Think about the same case that you have with Docker. If you run something and it's going to be powered down, if it is a BIOS, it will just power cycle the last state. But if it's a virtual machine, you will need a scheduler, so a hypervisor, or something that is giving you the ability to control the life cycle of that machine. It's not like Kubernetes, that you have a pod, it's killed, it's back. It depends on errors, but it's always rescheduled. So we have this limited automation on virtual machines. It's incompatible with Kubernetes workloads. So if you have a pod that is running in pair to a virtual machine, they cannot communicate by nature. You will have to elaborate a strategy to use effectively this communication as effectively available. And you see that there I put the operational hybrid workload reference. That is basically this kind of ability that you have between VMware and Kubernetes that are not the same context, that they don't share the network, they don't share the service discovery. If you have a DNS-based way of targeting resources, it will be a configuration different for both cases. So this is really something that if you run your own data center, you will need to solve somehow. With VMware or the other KVM options, it's possible to have something that is orchestrating that for you, but generally you pay for that, and you need a DevOps team or someone that is a system administrator really able to understand all of your reality, so that hybrid idea of a workload will affect consistently what is also your productivity. In challenges that we have here, I see that, again, repeating, VMware and QEMU KVM, so including QEMU KVM now, they lack the Kubernetes native integration. The management of operations, like I mentioned, it's a nightmare. You need specialized and focused people on knowing the problematic of your deployment, your use case, and if they quit the job, you will need to retrain the team to understand what you want to achieve from this kind of, let's say, configuration, management, administration. Then the resources. In a virtual machine, you say, okay, I need more or less one core CPU, one disk, I need that amount of space, but you don't have a way to constrain the resources like you could do, in example, in Kubernetes, with resource limits and specific details that are proper of a system that is scaling by default, by nature, and it's not just put there like my laptop is here. I have to buy more storage for reserving part of the disk. Instead, in Kubernetes, I can just create a persistent volume claim, and I will have the same result. And then at the end, right there, the performance. You know that if you optimize your resources in a context that could be virtual or physical environment, you can benefit from the resources that you can put on top of the system that you are running on and your applications. So your applications will run with the right amount of resources. Here you see how we can have management fragmentation. I added some points that you can read there that are briefly expressing how you can move from the inability of managing big unscalable system to gradually innovate and have a system where you can put all the changes that you need. Like in example, I put a reference to innovation challenges. When you want to adopt a new technology, that is the key focus of this, to do that on top of a virtual machine, you could need to reinstall the kernel, install new drivers, or do an upgrade of a version of something. If it's Kubernetes, generally you could have something like canary deployments, blue-green deployments already available because you are using the right tools. But in terms of virtual machine, you could be affected by the whole bundle of things that are written down there. I hope that you see them. It's big enough, yeah? And the part related to scalability, that is the last one, but not least consistent argument, is that you will be affected, also if you have a lot of resources, from the inability of innovating your strategy to come from what is a big system here with a centralized machine that is communicating to something that you have to administer. And also if it's containerized, you will have the inability to schedule the resources that are effectively available, also if you have the right size for your machinery and whatever you are having in the server farm. You see that in the animation there is how we can evolve this concept from something that is just containing everything, and this is effectively expressing how you can have your bundle that is with Kubernetes, KubeVirt on top of that, and you are the controller. So what is KubeVirt? It's an abstraction layer, it's a controller, an operator that is running on top of Kubernetes and that is understanding the QEMU principles for running virtual machines. It is understanding the KVM network and concepts related to the kernel abstraction layer for the resources, and it's also translating that for you, extending the Kubernetes API to manage these kind of resources that we will see in the demo. They are just available as custom resource definitions. So think about your virtual machine that was running on top of VMware. Now it's available in Kubernetes just using a YAML file with some lines describing this kind of concepts. The stability, I already mentioned that if something goes down in Kubernetes, generally it's rescheduled. If there are no errors, you can have this rescheduling that is available as the same resource. You don't have to restart, terminate, do these kind of activities that will require human intervention or eventually control workflow with some kind of specific tools. You have a unified management because you just have to learn Kubernetes, and we will see that the kubectl command, that is generally what you use on the command line to manage a Kubernetes cluster, is just extended with a virt subcommand that is translated also with a virtctl abstraction that is really easy to use. Unified management and cost savings. This is implicit. I will recall the cost savings because you can optimize the resources. Your deployments and availability for whatever you are doing is consistent, and you save money. Also, let's do a comparison. If you are not familiar with the current bare metal offer and you think about AWS, let's say that you are having a stack running on AWS and you are affected by the billing at the end of the month. In a ratio of 1/10, you could compare the same solution that you are running on top of a provider like OVH Cloud that is giving you bare metal, poor bare metal, or Rackspace if you have a little more money, and you will save tons of money yearly with the only thing that you will have to hire someone that is able to install Linux on top of a bare metal, with the IPMI console generally, and the ability to understand the concept of virtualization. So here is worldwide how we can say that KubeVirt wins and will win in the next future on top of the traditional virtual system. First of all, because it's flexible and the community is maintaining the project consistently, so there is a community of developers. It's a CNCF landscape project, very used from companies like CIVO or CIVO to maintain their deployments. There are other companies that are doing platforms like Quemby. A lot of realities that are already using KubeVirt to produce results that are available also as SaaS services. Then you have the communication. A part of the cost savings, you have support. You have a lot of options to create on top of the solution that you already run with KubeVirt, additional services, operators, scalability. Let's say that everything you can need for running monitoring, observability, it's already available because people that are using this are already creating on top of this ecosystem a lot of different options for you. And also, if you have some specific needs, you can ask to the people that are working on the repository of KubeVirt. It's already having around 800 contributors, a specific use case. They will work for that. Future-proofing, because it aligns with Kubernetes and CI/CD. So imagine that another interesting use case is that on top of your virtual machines, you want to include something like Flux CD, Argo CD. They are all tools for managing the continuous integration and continuous delivery. That will increase a lot the productivity of your teams because developers will be having their solutions already running inside a reality that is describing the emulation of a real production environment, and it's really not that costly as having it replicated on something that is an emulation. It's a real virtualization. The real world success, we will see that we have a lot of case studies where companies that were migrating from a use case of VMware or other virtualization to a consolidation of KubeVirt, they effectively were immediately noting the total cost of ownership was half. KubeVirt is a solution because we already see that it controls all of these things for us, and the enhanced scalability and flexibility, you will just have an idea of how having this port exposure, the ability of controlling the firewall, in example, think about a firewall on top of a Unix system. You will have to run IP tables, NF tables, or interfaces that are having that potential of managing your network configuration and similar. In Kubernetes, you do just network policies. So you don't have to know all the syntax of the firewalls. Same for Windows. Imagine the dream. You can disable the firewalling and have the network policies doing the firewalling for you. It's not the best practice, but it can be. Here it's describing basically how on top of workers and Kubernetes nodes, you can have this KubeVirt, the V that you have there, it's that logo, and mixed workload with VMware or converted machines, virtual machines, applications that are containing both virtual machines and containers, or just containers. And this translates in a distribution of your needs on top of the nodes that are running Kubernetes and KubeVirt. So distributing means scaling, means benefit from this kind of configurations that you implement on top of that. You see that, again, real-world impact, the legacy applications costs, scalability problem, and also productivity are completely gone. And we have an improved capacity of knowing what we are deploying. So it's like monitoring observability. If you are familiar with suites like, I don't know, an enterprise, New Relic, Dynatrace, whatever, you're sending a lot of data and you're not knowing what is your effective data and the need for that information, unless you start to classify. With KubeVirt, you can classify the workloads and have a big benefit from all of these things. Now we have finally the demo space. I will just describe what we will see in the demo because it will be quite extended. And I want to satisfy your curiosity also for the next questions that you will have. You see that in the right side of this slide, we have how it will be the system composed. I also have a video in the demo that I created because there are long processes like the disk conversion, the Terraform deployment. The demo is based on a Terraform stack that you will find on the GitLab repository that is also available at the QR code. But if you ask me, I will share that. The demo is running on an RK2 Kubernetes cluster. It's a special SUSE distribution based on a Rancher console. We will see the Rancher console. I've been using Longhorn as a storage class, so you will see something that if you are familiar with storage, it's an abstraction that you will say, okay, it's a RAID 5 because there are 3 replicas. It's something for the people that likes the screwdriver in a data center and changing disks the old style and the old way. Then we will see how we deploy the pods and components after seeing the Kubernetes cluster and how it's done. Again, Rancher Longhorn. KubeVirt installation, it's quite easy, simple. You just have to run the command calling the Kubernetes API with the manifest endpoint, but in the Terraform stack, it will be automated. So if you run that stack locally, you will have KubeVirt already installed. Container data importer is a concept that I will just spend 2 minutes now. In Kubernetes, you can have a container network interface called as a CNI or a runtime interface that is generally CRI. You can have CSI storage interface. And for KubeVirt, they implemented this data importer component that is nothing more than you have a disk of a virtual machine, you convert it, and you import it in Kubernetes as a persistent volume. So not being familiar with Kubernetes storage, just in 2 seconds, it is having persistent volume claim, that is the connection with your pods and your components, and a physical space where you have your disk image, persistent volume. The persistent volume is produced thanks to the container data importer that is generally using a quick code 2 as the format of the source disk because it's KVM QEMU based, and it is producing the disk of the virtual machine. The rest of the things is done by the KubeVirt handler that is running as a demo set. So on each node, there is a copy of the pod that is giving us the ability to provide this specific disk to virtual machine translations. And I will show you how you do the conversion, because generally if you find the how-tos on the internet and you follow them, they will implicitly say that you already know how to do a disk conversion. It's not simple, but it's not complicated. It's just a one single line command. Then to expose these services, since I'm working on bare metal and everything is running on my laptop, I will just show you briefly the inventory of my current resources. You see that I have an i9 processor with 24 cores and 128 gigabytes of RAM. That does mean that you have to increase the RAM capacity if you want to run the full stack, but it's not really needed because you can run the same thing with 64 gigabytes of RAM. If you buy hardware or you go for bare metal, you will just take care that you have enough resources to run a multi-cluster Kubernetes Rancher distribution or other distributions. And finally, the manifest and operator for VMS, I will show you how you can easily, very easy, describe how a virtual machine is translated in a few lines. So let's start from the next, it should be the video. I will, if the video is not working, don't worry, because it was supposed to be working for the case where we lose the internet, but I don't think it will be needed. So at the beginning, I'm just creating the Terraform stack. So it will be basically a Terraform apply. Okay, here you see that just posing, I have on the right the libvirt virtual machine manager that is a translation of a console. There is nothing running there, nothing has been produced. Terraform init is here for us because it's what we are going to apply after the plan to have this cluster up and running inside the existing virtual machine manager. Let's see if it moves. Otherwise, I will move it forcefully because it's just a helper. So here I'm explaining the plan. There are a lot of resources. I will show you just briefly the Visual Studio codes with the Terraform structure for this specific repo that I have created. And now scrolling, it's the plan. So everything that will be applied, I just did this in the video to show you that the complexity is full of resources. We are configuring storage. The token for accessing Kubernetes is really completed. There is also a version with K3S if you want to play with that in the repo, an alternative one. I created the storage. Now you see that I will apply the plan. And here on the right, you will see appearing the 5 nodes. So this will be exactly the same situation on your machine. The 5 nodes are starting up. I'm using Cloud Init for configuring everything locally. So you just run a cloud image of Ubuntu for this case, and it will create the whole stack. Here I show you how the virtual machine console is available inside Virt Machine Manager of QEMU. It will be the same like running the SPICE interface connecting to a console interface of the virtual machine. And it's familiar to everyone probably how you can access the console. And here is the description of the resources that I'm using. So it's a normal machine emulating a Q35 that is a QEMU specific base machine. There is no UEFI, but you can also emulate the UEFI machines. You just need to be sure that your host is transparent, because otherwise nested virtualization will not be possible. I am using 16 gigabytes of memory and 4 core of CPU for each of the virtual machines, and Virt.io with the basic disk mapping for drivers and similar for mapping the disks of the machine. Translating this to a real case here, what you are seeing is exactly what I have now running for the demo. So nothing different from what we saw here. And for the part related to the source that I'm going to show, they are not in the video, I started with typical VMware workstation downloaded from Broadcom. It's for free now. And creating a Windows server. Really? A Windows server. You will see a Windows server running inside Kubernetes. No Windows containers. It will be available. We will just show the Internet Information Service and eventually an RDP connection, but I don't want to do too much Windows. So this was created with VMware. It had a specific disk out of there. I haven't updated VMware because I don't want to use it anymore. It was just for this demo. And at the same time, in my virtual machine manager, you see here, I cannot zoom, but this is the converted disk of Windows. This is the Ubuntu that we will see it's running also as a virtual machine inside the Kubernetes cluster, the RKE2 one. And going back here in the video, this is the part related to the initial access that I did via SSH to the nodes. And on these nodes, there is a meta load balancer that will expose the services for us. So we will see that we are able to effectively see everything. It's really essential, but if you grab the repo, you will be able to run exactly the same things. So it will be very inspireful for many people. I think that there are not that much practical approaches for doing all of these stuffs all together without the problem of finding the documentation. I will just zoom a little on what are these commands. I cannot zoom because it's gedit. I should change editor, but I will describe them. This command that is available in a gist parallel to the repo is how you upload the disk that you created. And if we look at the terminal that I'm going to show you now, you will see how we have the size of the disks. So let's start from the disk of Ubuntu. Here I can zoom. Let me see if I can find the, okay. Now, what I will do here is just referring to the size of the disk. This is where I created a Ubuntu disk image. It's a quick code too. And you see that here I will have a 16 gigabytes of disk created. So I decided to use all the space. You can also let it expand as time goes by. These are the disks of the cluster. So RKE2 disks are here. You can see that the size is super compact because they are just an installer for the operating system. And this quick code 2 is the disk image for Ubuntu that we will see it's running as a virtual machine. I should also be able to show you the Windows one, that is this specific disk. Again, I will expand for you a little. In this case, it's a 13 gigabyte quick code 2 Windows 2000 server, but really it's 43 gigabyte because in this case, I didn't want to use additional space. I don't have specific plan for Windows here. And the disk is compact, and I used it to convert this disk to quick code 2 with the QEMU image convert. So I will not show you the commands, but it's a one-line command. You specify the source that was VMDK, for my case. I think that we could just see inside the Windows. Let me see if I can find it. Windows Server, yeah, this one. Here is the source. So the VMDK suite with the VMX describing. Again, I can expand here. You will see that if you are familiar with this kind of VMware virtualization, you will see the typical structure of VMDK. And using the QEMU image convert, you do the VMDK to the quick code 2, and then you just have the disk ready to be imported on your KubeVirt deployment using the command that I was showing here. And here, sorry again, because I cannot expand, but it's available in the gist. I will read it for you. Virtual CTL image upload. You specify the name of the PVC inside Kubernetes, the namespace at the end, various things like disk size. It has to be explicitly declared, the path of the disk. Lot of arguments that will be generally documented in the virtual CTL image upload subcommand. Thanks to the exposure that I did of the service endpoint via meta load balancer of the uploader, the CDI, this will target this endpoint that is specified here and upload the disk. It generally takes some time. I think that in the video here, I have a specific reference to this operation, and we have enough time to take a look at the elapsed things that are here in the video, so why not looking at them? Here, I'm just describing the meta load balancer address pool, so I decided to expose a pool of IPs that are really the same network of my machine for exposing the services like the upload proxy, that is what we are talking about right now, because it's the endpoint where you will upload the disk. I put an evidence on that here. And having that exposed, I can import the disk, and the result will be basically the fact that we will be able to NCAT to the port 443 of Kubernetes API, in this case. Everything will be describing that thanks to exposing these services for the upload load balancer endpoint, we have the port 443 working, port 443. And here, this is exactly the command that I was translating for you, the part related to the upload. We will see now that in the elapsed time, a disk of 15 gigabytes will be imported in 1 minute. So if you are impatient, you just have to go grab a coffee if you drink it, and you will have the disk imported. We will obviously skip the elapsed time. I didn't this for Windows because it was more time. It was 43 gigabytes. At the end, you will find the fantastic message that it worked. If it's the first time, you will probably light up a candle or something like that because it's really a great satisfaction. Now, apart of that, you will eventually, after having the disk inside, starting to look at the PVC, how it's done, things that we will see visually using the Longhorn interface. And here, elapsing the time and scrolling more on the video, now it's time to define a virtual machine. You see that in the whole screen, this is the manifest describing your Ubuntu machine. For Windows, you just have to do some other things, obviously. One is CPU exposure. You will need to extend the concept of a core that is really host-based, so nested in nested virtualization. Here we define the memory resource only and the virt.io disk. For Windows, you have to use SATA and the driver for the Ethernet 1000 adapter, because otherwise you will get crazy installing the virt.io driver in Windows. But basically describing the virtual machine with the describe command, this is the result that you will see once you have imported the persistent volume claim and the virtual machine is up and running. So the video here should come to an end because I wanted just to consolidate all the steps that were really time-consuming for us. Now we can go. Maybe there is something more. Let's see if the video is completed. Yeah, this is an access. So why not showing you something that you will see later, a virtctl command that is how to start your virtual machine here, virtualctl start. You have a VMI that we will see it's available. In this case, it's just for Ubuntu. It is running. It's how you see virtual machines in Kubernetes. Just one command and the status of how it is. And then, finally, now we do the VNC subcommand that will open a SPICE terminal. Now, just one time, this is the SPICE terminal. This is the user that I used at the beginning, but the password is Ubuntu if you want to hack it. And Ubuntu inside virtual machine. On top of this Ubuntu, I also installed, and I will show you now, K3S. So Kubernetes inside Kubernetes. Virtual machines inside virtual machines. Space for your fantasy. Whatever you want to do, it's really your limit. KubeVirt has no limits for this case. In the video, I haven't included, I think, Windows, because I want to show you Windows directly from my command line. Here I'm installing curl just to show you that if I query from this virtual machine the kubernetes.default.svc.cluster.local, which is the API of Kubernetes, I don't have to bother about service discovery. The virtual machine will understand the endpoints of the Kubernetes cluster directly from inside, using the same DNS. It's an authorized because I'm not providing the token. But if I install the K3s YAML or the kubeconfig file for accessing the cluster, then it will be available also from inside the cluster. Think about your developers will run a virtual machine for developing inside the Kubernetes cluster, and you will give them exactly that environment that is their workstation needs, and they have the ability also to communicate with the big cluster that is running their specific machine. So I think that the video is enough. I don't want to extend more the video. Yeah, you can go for a question right now if you want.
Just before I forget, would you be able to use like the big maps that are mounted to this resource back into the VM so you could do things like the service account access into that API?
Exactly. I have no case like that because I wanted to keep it really essential. But think about that whatever you do for a pod is your virtual machine. So role-based access control. In example, you do a service account with a specific kubeconfig to give that kubeconfig to the developer that is using just that virtual machine that you are running there. Inside the machine, it depends if you give to the machine the access, but it can be done. So on top of the manifest, it is really like a pod. I will show you the pod now. So first, let's go one by one with the things that I have here. First, the cluster. This is where we are running Kubernetes, and this is the RK2 cluster with 3 masters and 2 agents. I could have been doing just one node, but it's for everyone to play. They will be having a real case scenario. So you have, and it's nested virtualization. So this is libvirt. If you have money and you buy 5 OVH cloud nodes, you can have 5 nodes with real virtualization for the KubeVirt machines. It will have 10 times better the performance. Here I have the pods that are running. Second chapter for our presentation will be that there is also the monitoring. So I installed in another part of the repo Grafana with Prometheus. You install a node exporter on each node of the cluster, and KubeVirt is giving you dashboards. I also installed Loki, that is basically to see the log files inside Grafana. And one by one, look at Longhorn. So the part related to the storage, this is partial deployment of Longhorn, but we will see it in the UI. This is just for managing the consistent storage. You can also do that as a local storage single disk, but it's better to have it in RAID. So you will be sure that Longhorn is managing the consistency of your storage for you. Look at how many resources are here in this Longhorn system namespace. So there is time for additional presentations there. And here, the virt operator. So first, double copy of the operator. You know that the operator has a reconciler listening to Kubernetes events, reacting to that, and doing specific activities depending on the rest of custom resource definition that you define. The handler is a daemon set that is acting, controlling each node for the resources. Then there is a controller. That is basically the translation for the API to be creating virtual machines, reserving spaces, and similar. Here, when you install RK2, there are some jobs that are completed to install Ingress Nginx controller, Core DNS, and other things. And here, there is the typical Kubernetes rest of things, the kubeproxy, and part of the Kubernetes installation for RK2, the etcd cluster for 3 masters, Cloud controller, because I did it with a cloud image. Cert manager, why not including it? And the CDI, that is that container data importer we were talking, and the Rancher UI with Fleet installed by default, common storage interface, and Calico as the container network interface manager. As you can see, it's a lot of things. But they are bundled, and you will not bother about installing all of them if you have to follow the steps that I produced in the repository. One important thing, each virtual machine can be namespaced, so I can isolate one from the other. If I want to become a cloud provider or a provider for my developers, one single namespace could be for one or a group. In example, QA team will just see QA team. The machines running there will be isolated. I can create network policies, filtering by labels, annotations, a lot of things that we do in Kubernetes. And here the lin and win are two different namespaces. This is how you see generally the two machines running. The reason for why I'm running the command live now is because I want to be sure that everything is up and running. The ready true. There is another thing that we can do apart of getting the VM, it's the VM instance. So what is the IP of that machine and so on? Think about one important thing about the IP and network configuration. You don't have static IPs. Incredible. How can I manage service discovery without static IPs? Core DNS, Kubernetes DNS. Solved the problem of nights and days not sleeping and having a lot of coffee because of service discovery. And if you know Kubernetes, you know that this will be Ubuntu 24-kvm.vmlin-kvm.svc.clusterlocal or .whatever, and that will respond exactly to this exposed VMI, VMware instance, virtual machine instance IP. This is the representation of how you can expose a service. You see that I was mentioning earlier that we would have been exposing for Ubuntu something. Again, I will expand a little more. I can SSH Ubuntu. I can use the 6443, that is the Kubernetes API of Ubuntu that I use to install another K3S inside Ubuntu. And for Windows, we will see just the IIS, and the RDP, I will not connect with the RDP because I will use Spice. It's easier. These are, again, the disks that we saw earlier. This is the converted disk, and finally, we are reaching the window where we will connect to our virtual machines. Little bit of more size. VirCTL VNC to the machine of Ubuntu, enter. Here is our Ubuntu. This is a virtual machine running inside our cluster. I will just enter the Ubuntu password because it's safe. It should take not that much time. Okay, it's the first access. It's a virgin machine. This is Ubuntu. So you know about that. Let's open a terminal just to show you that what I was saying earlier is we become root because K3S is installed with the root credentials, and we do a kubectl get nodes, and this is K3S cluster inside Kubernetes. This is our friend Ubuntu. Now let's go for our enemy or other friends, Windows. It depends. Again, expanding this. VirtualCTL, Ubuntu, not Ubuntu, Windows. Faster than Ubuntu. Sorry for not paying the licensing. I just downloaded the part related to Windows. I exposed IIS. I will show you now IIS. This is running inside Kubernetes. No tricks, nothing. I could show you, but we will run out of time, that NSLOOKUP will give us the same Kubernetes default SVC cluster local and whatever other, it can intercept the other virtual machine too. So basically here we have the 2 spies option. I will remove both of them and I will give you the part related to the Rancher console. So if you use Rancher, you can use your workloads here, like if you are able to use K9S or Lens, something like that, use Rancher, it's better, it's already running inside. You have everything. You have a fantastic marketplace, so if you want to install your favorite NAT server instead of Kafka or Istio, you just click here and it will work. And then, apart of all the other things, it's not Rancher our target today. Longhorn, this is the storage interface where we can do snapshots. We have RAID 5, so if we go here to nodes, we see our nodes cluster. And this is like Portworx, but for free included in Rancher. These first 2 are the 46 Windows gigabyte, the 46 gigabyte Windows disk in RAID 5 with 3 replicas. And the other one is the Ubuntu one. I think that here we have IIS running on top of a exposed service. This is from Windows. This is me. Don't look at the face when I have my arms this way. And this is for another time. Go ahead with questions. I see one. And I will conclude the slides because otherwise we will lose a lot of contact with the rest of things here in the presentation. Go ahead with the microphone. Let me see if I can talk about the use case.
So if I understand this right, this is running on Kubernetes, and then how many pods are supporting the virtual machines? And then can you kill the pods and it still serves?
So
stability is what I'm asking.
I will give you a very, very brief answer just doing the pod enumeration. You remember that here I did a get pods-a. These are the 2 pods running the virtual machine. 1 pod per virtual machine. You can scale them up, but it does absolutely not make sense. Remember that they are connected to the persistent volume claim, so they share 1 disk. There is a way, and this is curiosity that you could ask for, to use a read-write many because of Longhorn, so you can have several pods accessing the same disk, and concurrency is managed by the NFS under the hood controller that Longhorn has inside. You can also use Ceph if you want to use Rook and shared access. But in that case, you will have to ensure that you have a read-only part of the operating system, like an AWS workspace, and the developers are using their own specific persistent volume claim. So that's up to you, really. It's full of ideas that you can implement on top of that. Go.
In the virtual machine manifest, how granular can you get when you create the virtual machine? Like specific?
Can you raise the voice? Because
in terms of defining like the instruction set for a CPU or PCIe device pass-through or per virtualized device that you want, how granular can you get when you define your virtual machine in the manifest?
So imagine what I showed you here about QEMU. Let's see together again an example of a virtual machine just to give you an idea. I will use the Ubuntu one. So I'm opening the part related to the resources. Here is the complete XML, if you want to do that, of all the resources, including things that we are not using, like a trusted platform module, emulation from the motherboard, whatever. All of these things can be translated to the CRD. There is a responding entry for everything. But I didn't implement the whole bundle because by default, all of these values are chosen by QEMU at the beginning. But if you want to be specific, you can really implement fine-grained virtual machine configuration And I will just show you the part related to Windows. So this one, sorry because I cannot zoom. Maybe I can, let me try. No. This is the Windows custom resource definition from here to here. And to show you the difference, I have a host pass-through here that I used. Here I have a disk bus SATA, a network interface that I had to define to use the bridge, nothing, Ethernet 1000. So all the things that you define inside QEMU are customizable. Go ahead.
I'm afraid we're actually out of time. We need to allow the next speaker to set up. But you can talk to Fabrizio in the hallway and get your other questions answered. Thank you so much for that presentation. That was excellent.
I've been happy to share the practical part because eventually the use cases that are missing, you will find them in the presentation available on the Git repo. Add me on LinkedIn. There is the QR code, but you search for my name. It's available in the scheduling from SCaLE, and you will have all the answers that you need. Please use it, because it's the future. Maybe one day you will remember me as the fortune teller, but this is the future. Congratulations, everyone, for having the patience. Thank you.
That was really excellent.
Yeah, and sorry. It was excellent.
Hey. Yep, test 1, 2.
Howdy, everybody. So next up, we're going to have Brian Honoff talking about using Nix to build smaller container images, which is, I hope, what you came in here for, and not the talk being displayed on the board out there, which is wrong. But maybe if you did come in for the other talk, stay anyway, because this is going to be pretty cool. So with that, why don't you take it away, Brian?
Yes. Okay. So I'm indeed going to be speaking about building what I believe are fairly small container images of Nix. But I want to have a bit of a history of why I wanted to do this at a cloud native track. I have given a version or variations of this talk at multiple Nix events or Nix-focused events already. And they all go pretty well, actually. I always get very good feedback. Everybody always agrees with me, and it's always amazing. And that's when I realized, like, oh, I might be talking to an echo chamber, right? People might be agreeing with me because they have already been sold the Kool-Aid. So who am I? I'm Brian. I'm a software engineer at Flux. Flux uses Nix under the hood, so that's fairly cool. You can find me at all of those things. Feel free to reach out to me. Flux also has a booth over in the exhibit hall. Feel free to come drop by, say hello. Nix and the NixOS community also has a stand over there. Please do go there. So, what is this Nix thing, right? Because first question may be, who here knows Nix? Drop your hand if you mean that you've heard of it, right? Or if you're actually using it, I guess. Are you using it, is what I'm asking. Okay, that's quite a amount of people. So keep it raised for a second. So the people that don't use Nix, if you're confused, look around, right? Ask the questions to them. Cool. So I always like to talk about Nix as this very overloaded term, right? It's a lot of different things. It's a package manager, it's a language, it's an operating system based on Linux, it's a whole new idea of doing software management and software deployment, and it's a whole new way of how software is built. There's a binary cache that's like the largest one in the world right now. It's like 120,000 plus packages or something crazy like that. It's a whole lot of different things. And then there's all these community projects that have Nix in their name somehow. So if you ask me what's Nix, my answer is yes. And it's pretty notorious for its steep learning curve. I do not believe there is a steep learning curve at all. I believe the steep learning curve is an illusion because you can approach Nix from so many different angles, right? You can use it as an operating system on your computer, on your servers and supercomputers. You can use it as just a package manager on your Red Hat Enterprise Linux, right? That's possible. You can just use the language, although I've not yet seen anybody do that successfully yet. But you can just use the language, for example, as a configuration language, right? To generate templates. That's possible. But for the sake of this talk, I'm going to be limiting myself to look at Nix as a way to generate Docker images, okay? So yes, I know that there's a bazillion things that are very cool about Nix, but for this talk, I'm limiting myself to just outputting Docker images, to keep it simple. I'm going to be using something that's called Docker Tools. That's a library that resides inside of Nix packages. So if you're using Nix and you're pulling Nix packages from the internet, you already have access to this. It's pretty awesome. But first, I want to show you some Docker files, right? Because this whole talk is about generating small images, specifically, or pretty small images. And I wanted something to compare against, right? Something to compare against that Upstream is already doing. So I have this fairly simplistic Docker file, at least I believe it's fairly simplistic. It's using Alpine. It's installing some package. I didn't know Kause was in a different repository on Alpine, which is a surprise to me. It doesn't have the hello binary, which was also surprising to me, so I just echo hello world, and then I create a small script that does hello pipe Kause. And if all goes well, you build this thing, you run it, you get a cow that says hello. Great, very interesting demo, I know, sue me. The thing it's about is the size, right? This image came out to be, at least as building of today, it might change in the future, it might have been different in the past, I do not know. As of building this today, it was 38 megabytes, or about 38 megabytes. Cool, not bad. But what if I use a different distro as a base image, right? That could influence a lot. Alpine's based on Muscle. If I use a different image, might be based on libc, might not be based on OS at all if you have a distroless container. So let's see, right? All of these comments, the slides are online. I invite you to read them. This was me questioning some of the decisions, let me put it that way. Even in a very small Docker file, I had a lot of questions about it. But okay, whatever, let's get rid of the comments. This is the essence of this Docker file. So we're running Debian stable. We're doing an apt-get update, apt-get install. This time we have hello and cause in the default repository. Great, I don't have to do extra work. I'm also creating my small applet again, and I'm running that whenever I run the container. Just as proof, it does actually run. It's 200 megabytes. Just to refresh your memory, the Alpine one was 38 megabytes. That's a whole lot more, just by changing the distro, basically, right? I mean, Kause and hello on most distros are not that dissimilar, but still we end up with a difference of more than 100 megabytes. Cool, Docker is great. I love Docker. I love it as a runtime. I love it as an ID. But honestly, I really, really like Nix, right? So let's go ahead and see the Nix equivalent now. Don't be scared. We're going to go through this. This is Nix code, right? It looks like JSON, or at least I hope that if you squint your eyes very hard that you see JSON in this. But it's really not that difficult to read. You have to take it slowly. So I'll guide you through it once. So at the top, we have this thing called an attribute set, right? And the attribute set you can identify by the squiggly braces. So on the left and on the very right, we have squiggly braces, yes? Everything inside of that attribute set is called an attribute. So we have an attribute called Docker tools, we have one named hello, Kause, write text file, lib, and shell. We'll see in a moment where those are coming from, right? But these are just, well, attributes of this attribute set. The little colon at the very end, at the very right, is telling me that the left-hand side, so the attribute set, is an input to a function that returns the bottom part. That's what the semicolon means, or the colon rather means, right? So I have a function that takes one input, being the attribute set. I very often read this as a function that takes multiple inputs, because that's what the attribute is, really taking one input, but implementation details. And then the bottom side is what the function will actually return, what it will actually run, right? In this case, it will return the result of another function, that being Docker tools.build layered image, right? So I showed you a little bit before that we are importing something called Nix packages that has a library function called Docker tools, and a function that's inside of Docker tools is build layered image. It does exactly what it says on the tin. It builds a layered image. There's also a build image function that builds, well, a container with one layer in there. So that's why I'm using this one, build layered image. We like layer caching, blah, blah, blah. Cool. This function, build layered image, takes as argument another attribute set. We can see that by the squiggly brackets. We give this container a name. So instead of naming the container at build time, which I find very weird always, you write a Docker file, but you never give it a name. You give it a name when you build it. With Nix and Nix packages and Docker tools, we give it a name when, at declaration time instead of at build time. Then we also have the same config options that Docker has. I am vague for a minute on what the actual document is called again, but the OCI has a document somewhere of all the different config options that a container should accept, right? And Docker adheres to them, Containerd adheres to them, and the thing over here, build layered image coming from Docker tools, also adheres to them. So config.cmd, those familiar with Docker files, no CMD, the no entry point, you have your user. We'll have a bit more of a complicated example a bit later where you'll see more of those options, or more of those config options declared. Cool, now I have this weird let thing, right? Let, and ignore everything that's inside the let and start reading it in again, right? So let, some garbage, and then in, and then we have this, I hope at least that it seems familiar, the square brackets, and then we're referencing the app. I'll come back to what the reference is in a minute. But so if you just in your mind delete everything within the let and within the in, you will see that this is the same thing that we did in the Docker file. If I go back to that real quick, there we go. It's like the entry point. I didn't use a CMD there. I don't know why. It was late when I created these slides. I'm sorry. So the entry point also has the square brackets and then the arguments that the entry point accepts, right? Nix has the same thing. There we go. Cool. Now, this let binding, right? All that's doing is giving me an opportunity to declare variables, basically, right? In this case, I'm declaring a variable app. It's calling a function called writeTextFile that, guess what it accepts? An attribute set, I heard it in the crowd, thank you. And that attribute set accepts as parameters a name, if the thing should be executable or not, and then the actual content of the text file that will be written to disk, right? So in this case, again, I'm doing the shebang to bin.sh, shell over there. We're going to see why I put it like this in a bit. And then I'm calling a library function from Nix packages again called lib.getexe hello. So what this is doing is lib.getexe is a function that doesn't take an attribute set this time. It takes what we call a derivation or an installable. For the sake of this talk, it's software. So lib.getexe accepts software as an argument, and it will return you the full path to the executable of that program. Because the hello package, for example, in Nix packages, could include more than just a binary, right? It could include the documentation of the package. It could include things that are needed during build time. It could include more than just a binary. So in this case, I'm just interested in the executable, so I ask Nix to do that. We pipe the result of hello into lib.getexe cause, exact the same thing as before. Cool. Now you're probably wondering what these dollar signs, squiggly lines are, right? These are references to other things somewhere in this Nix file. In this case, shell is referencing to the input of the function, right? Lib.getexe, well, that's coming from lib. That's also coming as an input. Hello is also coming in as an input. Again, lib.getexe and cause, both are coming from the input. And then app itself is referencing to the app in that let binding. So far, so good? Yes? Who did I lose? Yes? Okay, cool. The question was, it's a layered image, fair point. What's my base image? Nothing. The best way I can describe this is doing it from scratch. I'll get back into that a little bit later in the talk when I'm talking about the advantages, right? If you want to know right now, it's basically doing it from scratch. The layers are going to be determined by the software that I put into this container. And the software that I'm putting into this container is shell, hello, cause, and then all of its dependencies as well. Nix is able to just figure this out. Whereas with Docker, you would probably do a from Alpine, and then you have to install all of the software that you need, and that would then create all of your different layers, right? Nix packages' Docker tools will figure this out for you. The order of the layers that this generates is also deterministic. So the software that I put in, or depending what software I put in, it's always going to generate the same order of layers. So your layer caching should be fairly good if you use this approach. Does that answer your question? No? We're doing it from scratch and we're putting software in there. Okay, cool. Now we have the second file. We could have done it in the same file. I did it in the second file to fit it on a slide. You can imagine if I tried to fit this on a slide, it wouldn't have fit. Over here, we have a let binding again. We are declaring what packages is, right? So in this case, I'm importing Nix packages. I could have been more verbose and I could have pinned a very specific commit hash from Nix packages itself. In this case, I was like, nope, whatever my system has is good. That's basically what this is saying. So cool. Import Nix packages, call that thing packages, and then from packages, call the function call packages. This is a Nix packages implementation detail again, but it's just a very nice helper function that I will be using in the talk later as well, more extensively. Call packages accepts hello container.nix, so the path of the Nix file that I basically want to pull in there. It then accepts another attribute set, and that attribute set, I hope you can see hello, cause, and shell, that I also pass as inputs in the other file, right? Yes? Okay, can you speak up a little bit? Sorry. Right text was not there. That's a very good comment. So in this function over here, I am not declaring, or rather, when I do call package, right, there's a few things missing. And those things would be Docker tools, write text file, and lib, I believe. That's correct. What call package does is Nix packages knows of some of these defaults. So for example, write text file, there's a top-level declaration of all of the different things that Nix packages has. And call package is able to figure out, like, cool, if you don't pass me write text file, you probably just mean the thing that has the same name. So it's filling all of those things in for me. In this case, I am overriding hello and cause and shell. I could have left away hello and cause for this example, and it would have still worked, and it would have produced the same image at the end. Shell, I don't believe I could have left away because that's just not a default thing in Nix packages, or that's not a default package in there. So call package is doing some magic to fill that information in for me. That's a very good remark. Cool, ugly syntax, I know. It'll grow on you, trust me. It's JSON-like functions, but it can get very convoluted. It takes a while to get used to, but once you get used to it, it's amazing what it can do. Just to prove that it works, I built this default.nix, the default.nix being this file, right? So I build it, and then I docker load I for the file. Nix build by default produces the folder or file result. Cool. So I load that into Docker. I do a Docker run. My cow is saying hello again. Life is good. I'm happy. It's 160 megabytes. I promised small images. I am not delivering on the small images promise, but I tried. No, we're actually going to go a bit deeper. And this is why I did it this way, to split it up in two files. I'm still using call package, so this is the same default.nix from last time, but I'm just editing it, right? I still use call package, and I'm still using the exact same hello-container.nix that I declared with the whole function inputs and attribute sets and build layer terms. It's the exact same file. Nothing has changed. The only thing that has changed is that right now I'm going ahead and call it packages.packagesmuscle.hello. What this is doing, the previous example, this one, this was using libc, GNU libc under root. The default build environment for Nix packages is kind of tailored to GNU libc with configure, make, and GCC. That's the default environment inside of Nix packages, but it's fairly easy to override this. So over here, I'm going packages.packagesmuscle.hello.cause.busybox. So I'm using a hello binary that's compiled with muscle. I'm using a cause binary that's compiled with muscle as well, although cause is Perl. It will use then muscle to compile Perl and all of those things. And then busybox instead of bash. Okay? Just to prove again, it works. And if I could get a drum roll, it's still big. Right? I failed my talk. I am very sorry to disappoint. I should have consulted my colleague Tom, because literally I was in the exhibit hall 18 minutes ago, right before this talk started. And Tom comes up to me, I'm like, Tom, I cannot get this image any smaller. And he's like, oh, let me show you this one command that'll tell you exactly what's wrong. I'm like, cool. I should have had this, I needed this information yesterday. I will show you what Tom showed me, and you're going to see another cool thing about Nix. I died. Let's look at a more, what I like to call realistic, simple example, right? Why realistic? I don't know of any startup or enterprise company that is selling a hello piped into cause as a product. I like cause, I like hello, but nobody's paying money for me to run those scripts 10,000 times a day. And simple because instead of having two programs and having bash and needing an entire environment or core util, so to speak, I'm just going to focus on one binary, okay? Cool. What I'm going to be comparing against over here is the upstream memcached based on Alpine. Yes, that comes out to be 11 megabytes as of today running this on this laptop. Okay? This is the Nix file. It's big. If you go look at the upstream Docker file for this one, it's a two-stage build. The first one is based on Debian. It does a whole bunch of things for the configure script to run correctly. It then does a whole bunch of things to compile it correctly. It then does some cleanup. It does some optimizations. And then eventually it does a from scratch, I believe, or from Alpine, sorry. It does a from Alpine to pull memcached in, right, and run memcached that way. That turns out to be 11 megabytes. It's fairly large. It's not a very complex Docker file, but it's fairly large. Larger than this, at least. It wouldn't fit on this slide. That's why I left it out. So, again, what am I doing over here? We have our function again. This time, I'm only pulling in 3 things. I'm pulling in Docker toolslib and memcached, right? I'm calling the exact same function as I did before with Docker tools.build layered image, and I'm giving it a name again. But the interesting part about this, well, I'm going to make the middle part a bit shorter, just to make it a bit bigger, so hopefully it's a bit more readable. The interesting part about this Nix file are these lines, really. Right? We saw that we can have the config.cmd, so I'm starting at the bottom, but we can also set the user this way, right? Through Nix. We can config.user and then set the user. We can do config.exposed ports and then set the ports that we'd like to expose. We can also set the UID, the GND, and the user details, basically. And then if you go back to this fake NSS override thing, this is basically generating /etc/passwd and shadow. That's what that's generating, and that's the content of those. Those who know the syntax of it should look fairly familiar. Okay? So this is giving me a Docker image at the end that actually adheres to the best practices, right? First of all, I'm not running it as the root user, right? I'm declaring which port I should be exposing, and in a very weird, wacky, and taking a lot of indirections way, I'm doing a multi-stage build. Okay? Same thing as before. My default.nix now looks like this, where I do the call package, I give in the memcached container.nix, and then I'm setting memcached to use the muscle one. Could have used the libc one, but I want to use the muscle one because I hope that this will result in a smaller image. It's 5.4 megabytes when I built it. And it runs, trust me, I tested it. As far as I'm aware, 5.4 megabytes is indeed smaller than 11 megabytes. Does everybody in the room agree? I see a lot of nodding. Cool. I won. It doesn't run cow, say no, that's true. I'm going to stay on this slide for a little. What have I proven with this, right? Not a lot. I can generate small images with Nix. Cool. What I hope you can see in this slide is that if I had a memcached that my company had forked, right, and they were maintaining themselves, with Nix, this would have been, okay, sure, switch out the last part on the right, and you're using that memcached. There's very fancy ways to override inputs of this memcached. So I'm not 100% sure of what the actual dependencies are, build time dependencies that is, of memcached. But let's say it depended on OpenSSL, right? And for some reason, there's a security vulnerability in OpenSSL, as there sometimes tends to be, and I have to use the absolute latest one that I can get. I can override that OpenSSL. That's a very cool feature. If I now wanted to have this image, this memcached container, in just multiple different variations. Let's say that you have a container that you have per customer, and there's just this very small thing that changes per customer, right? In the Docker world, well, there's ways to pass the arguments in, but everywhere that I've worked so far, what they do, they just copy-paste the Docker file, they edit what they need, and they build it that way in CI. That's what I've seen more often than not. People don't bother with learning Docker file properly, let alone adhere to the best practices. With Nix, this would have been a second function call of the exact same file, thus guaranteeing that I'm building a very similar image in the end, right? This Nix packages thing is guaranteeing me that if I run this right now, and I wait 5 years, and for some reason I have to build this image again, it's going to end up exactly the same image. There's no question about it. Caveat, yeah? Caveat, not in this form. There's a different form of importing Nix packages that will guarantee that. This is now dependent on my system. However, I do not update my system for 5 years. There we go. Yeah, there's a different way to import it, but for consistency's sake, for conciseness sake, rather. Cool. That's what I can do with Nix today, right? I have what I find very nice language, because it's a fully fledged programming language. I can do a whole lot of things in there. I have a fully fledged programming language that I can use to build container images, and they don't even have to just be container images. I could use the exact same source code, right? And instead of doing docker tools.build layered image, I can output a VM. I can just output a binary. Heck, I can, if I really so desired, output a Helm chart that also referenced the Docker files or the Docker images that were also built through Nix. And I can interconnect them all, so that when I do Nix build, sure, the build is probably going to take an hour, because it's going to have to do a whole lot of work, but I press build, I go grab my coffee, and when I come back, hopefully it succeeded, and if it succeeded, cool. Now I have a Helm chart that I apply, it just works. But what does the future hold, right? I believe that Nix is capable of way, way, way more in the cloud native space. First thing is Nix Snapshotter. It's a tool that brings native understanding of the Nix store model to Containerd. What does that mean? Imagine that your manifests, right, the thing that you actually push into your container registry, aren't megabytes in size, aren't kilobytes in size, or like hundreds of kilobytes in size, but are like 1, maybe 2 kilobytes. Imagine that. They're very, very small. For your registry, they're very small. Eventually, when you end up in runtime, there's going to be there's some things that have to be done to write it to disk, and the actual container size will be larger when it's run, right? But it will only have, you kind of delayed when the pooling has to happen. You're putting all the information into just the manifest, you're not actually providing the blobs. You push that to your registry, the next time that you run it, Containerd is able to realize the Nix store paths on disk and bind mount those store paths inside of the container. A really cool thing, something I find really cool about this is that your layer ordering no longer matters then. Because you're just bind mounting store paths that are always unique into the container. So which order you bind mount them in, I don't care. Where layer ordering in some cases is very important, with Nix Snapshotter it just doesn't matter at all. Another thing that I'm looking forward to is KubeNix. So I have a personal vendetta with YAML files. There's a bazillion different ways to get around this. This is just an extra one. Instead of using YAML or another preprocessor, you can now use Nix to generate those YAML files for you. It can also help you with setting up clusters. There's a bunch of different things that this can do. It's just a very cool project, in my opinion. Then there's the place that I work at, Flux, right? It's one of the reasons why I'm giving this talk. The containers that we produce are about 300 megabytes in size. If you're doing anything useful, they're almost half a gig in size. I've seen them balloon up to 16 gigabytes in size. So again, this was for me a reason to go research, like, hey, are there ways that I can bring those sizes down? But we can take your environments, generate container images out of them, and you can do whatever you want with them after that. Another thing that I believe is that Nix should be a part of the CNCF. It can be located in many different places on this landscape. It can be your building, it can be used to set up your Kubernetes clusters, it can do a whole bunch of different things. It would be really nice if Nix would move a little bit into this place as well. Some downsides. I'll admit. It's very easy to create accidental dependencies. I'll show that in a little bit. You have to learn an ugly language, but you learn to love it, right? If you have ugly children, you still love them. If you're doing what I'm doing, you're moving a very fast-moving target called Nix packages. I'll show you, just because I can, how fast I mean. Oh, did not want to do that. Does that say mirror? Thank you. Let me exit out of this real quick. Where's Chrome gone to? It has disappeared. Great. There we go. If we go look, Nix fast Nix packages. What I mean by very fast moving, it's 746,000 commit messages at this moment. The last one happened 30 minutes ago, and there's a commit, every half an hour it seems like. It's a very, very active community. Let me put it this way. It's a very large thing because of it, but it's just a very active community. So if you're not careful about pinning Nix packages, you are going to be doing a whole lot of rebuilding. Where's my slides? There they are, cool. I don't have my speaker notes, so I'll just do this. Easy enough. Oh yeah, and you'll have to adopt a whole new way of thinking about how software is built and how it's deployed. What I mean by that is Nix works on what we call the store model. Every single piece of software that's on your system, that's built with Nix at least, will go straight into that store. But Brian, what about my /bin/bash, right? Or my /user/bin/bash? Well, those could just be symlinks. Whereas the FHS these days, more often than not, like for example, /user/bin is a symlink to /bin or vice versa. It's very weird. Nix just threw all of that out of the window and said, nope, we're throwing everything under /nix/store, and we're creating symlinks there where necessary. But it's a very different way of thinking about how software is built and how it's deployed. So that's, in my opinion, a downside, because that only makes the learning curve steeper. But in my opinion, the advantages outweigh the downsides. First of all, if you work with Nix, you are joining a very awesome community that is willing to teach you and talk about this for literal hours. Every time that I went to a Nix-based conference, the nights were not very early. They always extended into the night, and we were only talking about Nix. It was truly amazing. You are joining the largest package set in the world. Sure, Nix packages is very fast moving, but it also is the biggest one of its kind, right? That means that if you need a package, there is a very high likelihood that it's in Nix packages. Nix can be installed on your system that you're using right now, and on your colleague's system. And heck, why not your whole infrastructure? And why not pin Nix packages so your whole infrastructure uses that Nix packages, so that your developers are using the same dependencies as your infrastructure, and that if you have to onboard somebody, you are sure that their developer environments will work. You are sure that if they run kubectl apply, that it's not using a kubectl that's incompatible with the current kube API that you're using in production, because everything is linked together. It's a very awesome feat, in my opinion. And then I forgot all of the other things that I wanted to say, so I'll have to look at them. I'm sorry. Integrations with the cloud ecosystem are popping up left and right. Snapshotter, the Nix Snapshotter, the Kube Nix one, whole ways of setting up Kubernetes with Nix OS. Again, I believe we should be part of the CNCF. I believe that we should try and get in there, because we are doing a lot of cloud native things. You will benefit from the work that has gone into and will go into optimizing Nix packages. I was able to do packages.muscle.hello. I'm not sure if anyone has ever tried to compile something from source, once with libc and a second time with muscle. Raise your hands if you did. There's one hand. Nobody does this, and it's a very complicated thing if you have never done it before. There's very smart people in the world that do this, but with a Docker file, that information tends to get lost. With Nix, however, I can just go look at the source code inside of Nix packages and see what happened. It's a monorepository, literally everything is in there. Once your package is packaged inside of Nix, or inside of Nix, it doesn't even have to necessarily live inside of Nix packages. It has, you just have to package it with Nix. Doesn't matter anymore what you output. A Docker file, sure. A Docker container, sure. You want an OCI compatible container that just ditches everything that Docker ever said, sure, why not? You want a VM, sure. You want a VM with a different Linux or a very specific Linux, sure. You just want the binary, sure, why not? You want the binary and all of its dependencies, yeah, sure, we can do that. You package it once and output many times. It's a truly fascinating thing once you did it for the first time. And that's the advantages I think that I wanted to say. Yes, cool. There are some resources that I invite you to check out. The slides, by the way, are also on the website, the talk. All of the images should have a link attached to them, so you just click the image and it'll open up in your browser. The first resource, of course, is all the different Nix packages, Nix OS documentation that exists in the world. The wiki.nixos.org, I find a very amazing resource. Nix.dev if you want to learn the language. So there's Nix.dev and there's a whole language tutorial written by one of my past colleagues. It's really exhaustive. It's very nice. And then there's also just the website in general. If you go to, there's a little tab, Learn, where you can learn about Nix specifically, Nix packages specifically, or NixOS, if you're into that. So this is for learning Nix. There's also this blog post by Mitchell Hashimoto that talks about using Nix as a base image to build software, right, to then eventually put it in it from scratch. So if for some reason you are not capable of installing Nix natively onto your system or onto your infrastructure, you can still head into this route, where you still write a Docker file, but you're still leveraging all of Nix's benefits inside of that Docker container. This means that I, for example, believe that the Go way of building containers is amazing. You do a from Go as a build container, you try and output a static binary, you do a from scratch, you copy that static binary and the things that are necessary, and that's it. That tends to produce very small images. Now, imagine if this wasn't only the case for the Go ecosystem, but for your NPM ecosystem as well, for your Java ecosystem, for your C ecosystem, for your Bash ecosystem. Nix packages can truly do all of that. I just showed you the build layered image to build Docker containers, or OCI containers rather, I should say. But it's not limited to that. It can also build packages for Python, for example. And there's a very nice function that helps you with the most common things. The defaulting MK derivation, what we call, is set up for building C, for example. There's one for NPM. The NPM ecosystem is also quite exhaustive inside of Nix packages. So there's already quite a lot of language ecosystems that you can just use and benefit from today. Then there's also this blog post that I encountered randomly when I was creating this talk. And this talks about how to debug containers that are distroless, right? That don't from Alpine or from Debian. To come back to the question of like, what is this base image coming from? There is no base image in this regard. You can use that image as a base image afterwards, but there's nothing that we're starting from. There's a way to have it start from something, just not something that I showed. But of course, if you have a distroless image that doesn't have a shell, it's quite difficult to debug. This slide saved my ass many times during the creation of this talk. It's like 5 different ways to do it, but one of them is really cool. And that was basically the theory side of things. There was one more thing that I wanted to show you. And this is probably not readable at all from the back, right? Yeah, we're going to make this way bigger. Is that better? Yes, no? Cool. So, you might remember during my talk, this one container was larger than I expected, the Kause one, right? And if I were to dive into that one just real quick, that would be this one, yes. So give that a second. That should be in my system. There we go, cool. And I just scroll in all the way, because I don't really care about the layers. What I do care about is, first thing you might notice is that the only thing in this container really, this word, there we go, is the Nix store. That's literally the only thing that's in this container in its file system. I don't need anything else. The command of this container is referencing a store path in that store directly. So you don't need to put it in /bin or something like that. We just know the store path. Anyone know a way to hide the left pane? Otherwise, I'll have to make it a bit smaller again. And you'll just have to trust me on what I'm saying. This is the container that was built from muscle. Oh, wow, of course you do that. Okay, I'm just going to select it so you know it's there. Right. But for some reason, it keeps shifting everything to the right. Didn't do this before. Really? Okay, this will have to do. This is the image that was built from Muscle. So the thing on the right that I've selected right now is the store path to the Muscle static libraries, right? And if you go, Bash is still in there. Why is Bash still in there? The first time that I saw this, this makes no sense to me. I specifically asked it to use Muscle. I am not expecting Bash to make its way into this final image. There's also glibc in there, which I'm using Muscle. Why is glibc making its way into this container again? Those were the two that just dumbfounded me, so to speak, and that's also, if I managed to get rid of them, I would have been smaller than the upstream image. So, my good colleague Tom, a few minutes ago, taught me, and I'm going to teach you as well, this command. So this is a command that says nix y depends. Should have known about this command. It does again what it says on the tin, right? And in this case, I'm asking it like, hey, so, you know, remember when I do nix build with the Docker tools thing, it generates this result file by default. So I'm asking it, why does this result file depend on, and then the store path to bash? The one that you just saw in Dive, or at least I saw it in Dive, you probably didn't, but you know what I mean. And then I'm asking it to give me all of the reasons and be very precise about it. So if I run this, what you're going to see is, over here we see Kause. Cool. And over here we see that the CMD part of the declaration depended on Kause. This makes perfect sense to me. But then bash is over here as well. Now where's bash coming from? It's coming from Kause. So Kause is the reason that bash sneaked its way into this container. Cool. Why is that? Well, is this the one? Yep. That's because, if we go look at, again, this is just a Nix file. This is the actual Nix derivation, what we call it, that builds Kause. And if we go look at it, right over here, we have this thing called a post install. So we have built the software successfully, and now we're going to do some extra things to it. And in this case, we are going to wrap the program. Guess what wrap program does? It pulls in bash to create a bash script of our Kause to have a suffix for the cow path in there that references to something. So why did it pull in bash? Basically this piece over here. Is this wrong? No, I was just stupid and I forgot to check the source code of the package that I was pulling in. That was my problem. I could have also known about this command that would have told me literally why it was pulling it in. Then Tom also told me about this cool PR that just got merged. So one thing right now is if you generate the Docker container, or the container in general, sorry, with the Docker tools, stream layered image or build layered image, the order of those layers you can't really control. There's an algorithm in there that does it by default. This pull request gives you the power to mess with that ordering, to merge certain layers together that contain certain programs, for example, or to just like, I don't know why you want to do this, but like reverse the order of the layers as a possibility. There's some examples down here if you scroll down. It was a fairly good one. Is it this one? Yep. So for example, this would be a rule of how to order these things. In this case, it gets every subcomponent of Python 3, puts that in the same thing, and then for all rest, all of the other layers, it pipes it into a popularity contest, and it limits it to 100 layers. Popularity contest is the default thing that's used right now, to this day. We can also control the layer limits right now today, where you can say like, hey, I just want one layer, I want 10. There's multiple reasons why you want to be able to do that. And I'm honestly open for questions right now. Thank you.
Hi. So you did build an image, you measured the size, then you did use different packages, and then you did this discovery about how Kause is pulling the bash. So this is a lot of knowledge and understanding of the system. Of course, if you just, okay, I just want to do that for my software, I might not know this or might not be able to figure out or how exactly do that. So is there some tools to help me like understand what the size is going to be? Like does Nix package just tell me what the size of this package is going to be, if there's some options, things like that?
Not natively, no. but there is a way to ask, you had a microphone, I'm used to repeating the questions, sorry. Natively, no, at least not that I believe. Tom just walked in, so maybe Tom knows. Is there a way to ask Nix the size, like, of a resulting thing beforehand?
I'm not understanding the question. Well, the build could obviously change it in lots of different ways. So usually to find out the resulting size, you have to have already built it. But you can kind of have a lot of the components already built before you compose it into the final container. And so then you can do the math for that if the components are built, even before the final thing is built. That's the best you can do, just because compilation options can easily change the size or whatever. Yeah.
It'd be a bash script, I believe. You'd have to write it yourself.
Well, you could build all the subcomponents and then just have those be added up without building an image. Yes. The individual components, all those and their closures is all defined and captured statically. We could follow up.
Cool.
More questions?
Hi. Yeah, I didn't quite understand the popularity contest piece. Could you explain that?
You mean this, right? Nope, this one. Yeah, so the popularity contests, I'm quite vague on the details as well, but the way that I understand it, it basically gives the most popular packages. For example, libc is quite a common dependency of a whole bunch of different programs. It tries to get that up in the layer in the layers. So it tries to have that as one of the first layers that there is. Or for example, OpenSSL would also be at the top more often than not. So you need to contest to try at least and get as much caching and cache hits as possible, so that the different containers that you build with Nix, right, the layer order of them should be quite similar more often than not. If you're, for example, let's say an NPM shop, right, you write JavaScript for a living, NPM, or Node.js rather, is going to be one of your dependencies, right? So Node.js should be one of the first layers for all the different containers that you build, right? If you don't have the popularity contest, you're not guaranteed that it flips to the top.
To extend on what he was saying, you also have to take into account, it wasn't mentioned explicitly, I think, that OCI images can only have 128 layer limit. Mm-hmm. So if you had a thing that had more than 128 items of things that were coming from the Nix store, you're going to need to start compressing some of them together into layers, and you wouldn't want that to be like GCC or like libgc or glibc, mm-hmm. things like that. I had another point and I forgot it.
Yeah, but it makes sense. So with the default setting on the layered image function from Docker tools, that's set at 100. So it generates 100 layers rather, and every single layer contains one piece of software. And then the very last image, if there's more than 100 images that it would have needed, it would have compressed them all into the final image. That's the default behavior. Whilst over here you can say, hey, no, all of the Python dependencies make one layer out of that. Just gives you a bit more flexibility in the whole process of building the layers. Does that answer your question? Okay. Cool.
Another question?
I have a question. When did I lose the audience? Was it clear a little bit? Yeah, cool. One of the reasons I want to give this talk is there was a question earlier about where do I find more information, or something that I get out of it. It's like there's not a lot of examples for this type of stuff, right? There's ample examples for Docker files and Docker. There's not that many for Nix and Docker tools and build layered image. I hope that this will be, an example, and I hope many more will spawn from this. So that's, you can always help with that. Yes? Oh.
I got here late because another talk didn't go off. Did you show a URL for the slides?
For the slides, it's on the SCaLE website. So if you go to SCaLE, and then I'll go through this way, floop, there we go. It should be right there.
Okay, any more questions?
Yes, one right there.
Hi, thank you. So question, the whole process is really good to someone who understands it, right? So if you have a developer that's pretty competent, comfortable with the process, tinkering, no problems. But if you have a group of developers that just want to come to work, build a bunch of containers, and then go back home, they don't have a big appetite to learn something new.
Could you hold the mic a bit closer?
They don't have, if you have a group of developers that are not very interested in learning a new skill. Does Flux, for example, simplify the workflow? What would the workflow improvement be to accomplish this?
Flux in this scenario simplifies the experience of it, so to speak, right? It simplifies, we're biased in that sense. We set up a very biased way of calling these functions. Yes, we make it simpler to get going at the expense of larger images. We're looking into ways where we can make it smaller. Is it even maybe necessary to make them smaller is another question that we're asking ourselves. On average, I've seen them, again, they range from 200 to, I've seen them be like 8 gigabytes in size. Depends as well what you're doing. It makes it easier because you're not exposed to the Nix expression language with Flux. You have an imperative interface where you do Flux install certain tools, and then there's a command Flux containerize that outputs the container. That answer your question? Okay, thank you.
I have one real quick. So automating the choices that you made would require actually doing some exploration or speculative execution of the actual code that was going to be used, right? Because like, for example, say that there was another version of the KubeVirt package that did not wrap bash, right? You don't know that you can, like an automated installation program doesn't know, or a container builder doesn't know that you're not going to depend on the access to bash ahead of time, right? Unless it actually has, unless it actually executes the payload of the container.
Mm-hmm.
Is that something anybody's working on?
Could you repeat the question one more time?
So like I was thinking about how you would automate this, right? Like how you would automate the choices between different versions of packages, et cetera, in order to, say, get the container smaller or fulfill some other goal. And I was realizing one of the problems is that, the way that you did it is that they're human choices, right? You know that all you're going to be doing is calling KubeVirt from outside the container, and therefore it doesn't actually need bash. So if there's a version of the KubeVirt container that does not have the wrap command and thus is not embedding bash, you can use that and shrink the container. But the question is how an automated container builder could know to make that choice.
I'm not sure. The way that I figured this out is, again, gut feeling. It was bash is not supposed to be in there if I'm using musl, and if I'm using BusyBox, I'm not expecting bash to be in there. Tom then showed me a command that explained why bash ended up in there, so that's fairly nice. But I don't think an automated tool can know if it should be in there or not, if that was your question. It depends on how things are built, right? If you go look at how KubeVirt is built in the upstream Alpine package, it's going to be very different than how we build it, and how Ubuntu builds it, and how Debian builds it. It depends, I think, but I do not believe there could be an automated tool that would be like, hey, there's a dependency in there that shouldn't be in there. There is this thing in the Nix ecosystem called Hydra. If I could type. There we go. And this is our CI system, and one of the things that it has, if it loads eventually, one of the things that it has is a pretty graph that shows you the size of the binary over time. So one thing that you could do is set up an alert like, hey, if the binary size all of a sudden goes up by 300%, something has gone wrong. That could be a form of automation, but just like knowing it, I don't think so. Okay?
I was just going to follow up on the answer. There's also a thing in Nix packages where you can say, if you know that you don't want bash, for example, or glibc, there's a feature to say, require that this package build doesn't have a reference to, say, a specific package. So you can say disallowed requisites is like bash. And so if you know from up front that you don't want bash, you can have the system check at build time that bash is not a runtime dependency, and then it'll error out. But that doesn't solve it got 300% bigger, I don't know why. You still need someone to figure out why that happened. But if you know up front that I don't want glibc or I don't want LLVM or whatever in the final thing, you can statically say, check that during the build time. So does that, yeah.
I thought I saw another hand back here. Yes.
Oh, can I ask a question? I'm wondering what sort of additional optimization passes could you foresee Docker tools being capable of doing?
For Docker tools specifically, I'm going to be honest, I'm just a user, so I have no idea what other directions it could go into. One optimization is not really a Nix packages thing, but if Docker or other container tools could gain native understanding like Nix Snapshotter provides about the Nix store, that could be a form of optimization. Another thing that is constantly happening inside of Nix packages is just general optimizations of the standard environment that will then result in smaller binaries. There are certain flags that you can enable inside of Nix packages that will use like host-specific optimizations, but that's not reproducible, so that's disabled by default, but that could potentially reduce the size as well. That would be about as far as my mind goes. Does that answer your question? Okay.
Okay, we have time for one more question if somebody has one more question. If not, there we go.
Do you know if Docker tools currently support the button that's common in Docker files when you have a build image and you do not want to, because if I imagine I don't want to maybe publish Nix package in the public repository just for my build, for my binary being built.
Yeah, it does, and that would be this part over here, from image. So you can tell the build layered image like, hey, use this base image and go from there. There's also a way to chain these together. So you can do a weird multi-stage build in a Nix native way, but this can reference an image that's coming from Docker Hub or some other registry. It's not a directing, so you don't give the image name over there. There's a, okay, sorry.
I was talking about the build image not as a base image for what I'm building, but I want to build my binary. I don't want to publish it to Nix. I just want to use it in the thing I'm building. I might pull some dependencies for it and so on, but I'm not going out of published things if I'm building my thing.
I don't think I quite understand the question then.
It doesn't by default go to Nix packages.
Oh, yeah, it doesn't publish by default. You can set up Nix to pull from private registries, yes.
It does not publish.
I do not hear you, I'm sorry. Yeah, you're not always publishing to the cache. Like everything that I did in the demo stayed local on my machine. Yeah.
Okay. Okay.
Okay, yeah. That makes more sense.
The question was more like, can you take the calc modified to remove the bash, and then use that calc without having to publish the new calc?
Yeah, that's all on my system. Even the building of that package happened on my system.
Yeah. Okay.
I did not hear
I
the
think-
last thing you said.
Okay, and then we can they're continuing that discussion, and we are actually out of time.
Sure.
So thank you very much for
Yes,
an
thank you.
excellent talk. And you don't need to go anywhere, folks. In 15 minutes, we will have our last presentation of the day, which will be on the details of resource management in Kubernetes and how to use it effectively. So, take a quick break, but come back.
Hello? Yeah, they got me. I can hear it.
Say that again?
I can hear it.
Yeah?
Yeah.
Yeah, well, you can hear it.
Can
but-
they hear it? Can you guys hear me? Yeah.
Okay, there we go. Okay.
There we go.
Okay. Okay, one more minute. Hey, folks. Last talk of the day, but it's an exciting one. It's about scaling Kubernetes, right? Because that's why we're using Kubernetes after all, so you can scale it. So Joe Allen is going to share some of his experience in how to scale Kubernetes and how to do it right. So welcome, Joe.
Thank you. Nope. How about now? There we go. That is the way. Sorry about that. Well, welcome to scaling your Kubernetes clusters without going broke. I have an introduction already. I'm the site reliability engineer for Subsplash. Most people probably don't know who we are. We mostly do software for nonprofits, websites, mobile apps, and a lot of video streaming, which is kind of what led me to this conversation. Before I continue, I just have a quick question. Is there any Lakers fans here? No? Okay. I'm going to represent then. I figured there wasn't, because if you were a true Lakers fan, you'd be watching them play the Celtics right now. So what led us, and me here, is my team and I, probably like a lot of you, have noticed our cloud infrastructure spending kind of going up and up. And we looked at various ways to take care of that. Like I said earlier, we do a lot of video transcoding, and I don't know if any of you have looked at the prices for GPU nodes on AWS. It's pretty expensive. And so we worked through this to kind of try to see what we could do to optimize that. I'm going to kind of just go over just an overview of what the standard setup is, if you're using HPA, VPA, cluster autoscaler, a little bit of understanding of the unique issues with using those, what the solution for me, like I said, if you guys read the description, it's going to list Carpenter. So how to use Carpenter, the best practices within optimizations for it, and we'll go through there. And now that I'm looking at this does not look like the right deck, but we'll make it work. So typically, you know, with your setup, you're going to have a horizontal pod autoscaler. It works really well with cluster autoscaler, but I don't know if you guys have ever really dug into how the topology of your pods is working. But you know, like you want to be spread across as many zones as possible. It works either with cluster autoscaler or without. However, to do it properly, it's a lot more work with cluster autoscaler. If you don't do that, you do cluster autoscaler, you're going to get, you know, you might need to be in zone A, but it's going to try to automatically put your nodes in a balanced across the zones. So the new node may be in zone C. There is ways to do cluster autoscaler without that, but it is a lot of work. Second case, which is my least favorite case, is vertical pod autoscaler. You know, I guess I should probably point these out. Can you guys, do these flows make sense? HPA, it's reading the metrics, it sees you need a new node. Replica set increases it, you get a new pod on an existing node. Vertical pod autoscaler, same situation, but it may determine that you need a smaller or a larger pod. Maybe your pod had an kill, what have it. But the concern with VPA, right, is, okay, well now your pod needs more memory. Is that pod going to fit on a node you already have, right? It's very constrained to what you have, because with cluster autoscaler, you have to be pretty explicit. Also with VPA, it may not actually even end up on the same node again, because it's going to basically force your pod to it's going to kill your pod, and your pod's going to come up somewhere else. There are features for Kubernetes to work around that for the in-pod update for resource requests. However, if you're using AWS, they don't have that feature gate turned on yet, but it will be coming soon. But even if that was the case, vertical pod autoscaler has not been updated for that. Now, with those combined, when you're using cluster autoscaler, like I said, it's very constrained. Normally, you're going to have either, if you're doing it properly, you're going to have multiple policies, one for each zone. So you basically have an autoscaling group for each zone. It doesn't work well if you don't do that, because as I said, by default, you're going to have 9 nodes. It's going to put 3 nodes in each AZ. But maybe because of your topology, you actually need an extra zone somewhere else. The other issues with it is the instance types are very inflexible. You basically are going to have an ASG that's going to have nodes that basically have the same CPU and memory. And if you need any deviation from that, maybe you need another autoscaling group for nodes that have GPU. It's going to be another autoscaling group, and it's going to just keep going up from there. If you want to add spot capacity, that's another dimension for autoscaling groups you're going to be setting up in cluster autoscaler. Typically, with this setup also, you're going to have very low cluster utilization. A lot of nodes are going to be half empty, and it's just not going to be able to balance it right, because even though you have a new node, depending on your affinity, the scheduler may not actually have used it for that particular case. And because it is using ASG, it is notoriously very slow to scale. That part about VPA may break a working deployment, that was kind of what I talked about earlier, is that it's going to update your resources, but there actually may not be a node that you have that even can support that. And last, it's kind of very slow for innovation. Depending on how you're trying to set up your groups and your nodes, you may have various reasons to try to separate them. Maybe you're trying to isolate different teams, right, so that they have their own auto-scaling group. Or you're just trying to isolate expensive resources. That's another another dimension for how you're going to have to set up your auto-scaling group. You end up getting tons of them. And a new team comes on, or they need a new type of node. Somebody has to go in and update this now massive list. And this slide here kind of demonstrates that, right? If I want, I have some R nodes for AWS, right? I have a ASG for memory, for Spot, for on-demand. I have one for, if I'm doing compute, one for GPU. Maybe you have some high network workloads that need a very specific node. And maybe you have some that need either like an NVMe or just have a higher EBS throughput. That's another one. And you're going to replicate that across the AZs. And this is a lot, even without considering the fact that if you're going to try to keep teams isolated to their own ASGs for whatever reasons. Usually it's because you don't want one team using up all of your capacity if they have a bug or whatnot. So, I know this is very high level for Carpenter. I'm not sure how many people are familiar with it, but I will get deeper in how to do this. With Carpenter, right, it's going to work very similar to how Cluster Autoscaler works. However, if you're watching it, I'd probably wait for it to restart in a second. You're going to have some new nodes show up. Scheduler is going to recognize they can schedule them. It's going to put them into a pending state. The other ones are going to go into unschedulable. It's going to put the ones that it can schedule on that node. And then Carpenter, rather than using the ASG, it's going to work directly with the EC2 Fleet API to provision the cheapest node that it can pack those on. And when Carpenter does that, it's going to then compare not only that, but then 59 other instance types that are larger to see what it can get for the best price to fit on there. However, if it is spot, and you have this configured for spot, it is going to basically do the same thing, but also look at other dimensions, such as like how frequently are these nodes disrupted, and it's going to try to find the best balance for price in that case, so you aren't getting a spot node that's going to go away in a couple of minutes. Did I hit the wrong one? I was on the same slide. Okay. Sorry, I went out of track here. So like I said, the solution that I found, I think Carpenter is the best case for this. It's not going to support everything I wish it does, but you're going to get at least the minimum of what you would get with Cluster Autoscaler with some additional benefits. It can significantly simplify your configuration. So before, when I was showing you guys the AZ slide, this one, this would only be a couple of node pools with Carpenter, and I'll go over what a node pool looks like. Basically, though, it's going to look at your pod definition and make sure that you're getting the right AZ. It's also going to look at the fact of like how much memory you need, whether you need CPU, network, and you're going to get the right node for the cheapest price. So it's going to, like I said, it's going to choose the cheapest one. It's also much better at Cluster Autoscaler for consolidating nodes. So in the Cluster Autoscaler case, right, when it goes to consolidate a node, it may pick the one that has the lowest utilization, but that may actually mess up your topology for other pods. It may break other things. It probably isn't going to be what you want. If you do the version where I said you have like an ASG for each AZ, it is better at that, but it's still not going to be perfect. And Carpenter is open source. It was donated to the CNCF in 2023. Primarily, it was made by AWS and donated. So AWS is the primary provider you're going to find most of the documentation for and examples. There is a provider for it to work with Azure, and currently the GCP one is still in progress. But I really expect this to take off, especially, I don't know how you guys, your bill is, but like ours is crazy, and I would expect probably like half your bill if you were to switch to Carpenter versus what you had before. And I'll kind of cover some of our case and what we got out of switching to this. Yeah, so kind of worked around, sorry. So how many people here have used Carpenter or are kind of familiar with its CRDs? All right, that's a good number, cool. So like I said, this is still just kind of high level, and I'll get some detail later. So there is another CRD, but for what you guys will be using if you're trying to use Carpenter, these are the main two. EC2 node class is really going to be like how you define what AMI you want to use. There's basically, you're going to get 3 built-in ones, AL2, AL2023, and Bottle Rocket. I think AL2 should go away. AL2023 works great. However, if you guys are using something like Cilium, Cilium isn't compatible with that. You'd have to switch to Bottle Rocket. The other benefit of going to Bottle Rocket is it does come with the NVIDIA device plugin already there. So if you guys are trying to use GPU stuff, you don't have to run a separate workload to do that. I would still probably recommend it just because you guys can adjust how it does slicing for GPU. but I'll kind of go over that slightly. One thing about this is this line right here where it says AMI selector terms, and I'm showing latest. Please don't ever do that. This is a slide, an example. The aliases are there. You want to pick one that has, like, if you're using AL2 or AL 2023, you want to use the ones that have, like, the date alias, because it'll work for ARM versus AMD 64. If you're using Bottle Rocket, it is slightly different, and I'm drawing a blank on the way it is. I think it's just a version number. But you'd have to go look to see what's in that's AWS, of course. For a node pool, I'm going to go over deeper detail on what the node pools do, but this is the basic setup. Oops, sorry about that. You're going to have, just give it a name, you'll have a wait, and waiting is used when you have multiple node pools, so it's going to give you one of them will take precedence over another one, and I'll go over a case where you're going to want to use that. And then, sorry, the requirements are basically, you could think of them kind of just basically like a Kubernetes selector. Carpenter's documentation is really great for this, where they list out all the different labels you can use. There are some Kubernetes native labels you can use, like architecture, but most of them are going to be like, it really breaks down like the instance types. So you can either say, like, I want an instance category, and here I have compute, general, and memory listed. They have another label where you could do, like, I want to have a C6 node, right? Or you can do the whole family. But they break it down into labels like this. So this pool, depending on, you know, how Carpenter is going to see the nodes it needs to create, or the pods it needs to create a node for, when it tries to bin pack them and figure out the cheapest node, it's going to be able to leverage a C, an M, or an R type, and it's going to want the generation at least like a C4, or greater than C4. So it would be C5 or higher. And then the last bit, like I said here, I'm just doing AMD 64. One thing, if you notice with this, this would do, you know, C5 node, C6, C7, C8. It's going to do any of those. It'll do the network version or the regular one, depending on whatever is going to be cheapest and what you need. So I have a much more flexible configuration for my nodes here, because I could basically cover almost all the cases I showed before. If you noticed, I don't have the capacity type in here, which is going to be for spot or on demand. So this would also work for that case. When Carpenter is going to get a node, if you have spot and on demand together, you don't have to do anything special. It's automatic. It's going to try to find a spot, and it'll fall back to on demand. So pretty much one configuration can cover a lot of cases. You probably don't want to do that, though. You're probably going to want to pick one of these 3 strategies. This first one, like I said, does work. And that last slide where I said that pool was for AMD 64, if your workload supports ARM, I would recommend you try to take advantage of it. The AWS nodes with Graviton are probably like 15% cheaper, and they have a slightly better performance. But even if you end up not getting a Graviton node, the fact that you're looking at them, you're going to have a better chance of getting a lower priced spot instance. But there is some issues with doing that, right? Like, you either have to support both, or you have to make sure that you're restricting what pods can do. So typically, I wouldn't use the first, you know, the single pool. You're going to want to use either a multiple pool or a weighted pool. Multiple would be the case where, like, you're trying to isolate for either just, like, I have Prometheus on a node, right? I don't want workload schedule of Prometheus. I don't want any issues or instability with there to bring down my observability for the cluster. So those kinds of cases, you're going to isolate them. You may do team isolation. I would recommend, if you're doing Carpenter, pretty much there's always going to be a case where you have a pool that's at least shared amongst a couple of teams. And because of that, right, you don't want one workload using up all of your capacity. So I'd highly recommend that you guys do resource quotas for your namespaces so that one team just can't go crazy and use up everything. And then the last case is mostly when I use weighted pools, I would use it for if I'm trying to just split up my pools. If you're going to do reserved instance or savings plans, You want to make sure that you're using the nodes that you for those savings plans first before you go to any other nodes and you get spot. It's just, you have to make sure that you're getting your hourly commitment for savings plans. Saving plans also are a little bit trickier in that regard, is because the more explicit you are with what type of node you want, the cheaper the discount's going to want to be. And so if it can't go into that pool, you want it to be able to go to a fallback pool. So you have to be, you want to be very, you want to be explicit with your savings plan if you can, but like I said, it has to have a higher priority than the next one. And I'm going to go over what that would look like in a minute. 100 different node types with AWS, and I think it's over 700 when you consider like the size of the node. And if you can think of like trying to do all of this where it covers that depth, you know, and teams and everything else, it is going to get kind of crazy. And so that's one of the main reasons, just for simplicity of configuration, I would use Carpenter. So in this example, I'm just having savings plans for a particular C4 node. I wasn't explicit on the size. I want to weight that as my highest weight so that it comes out of that pool first. There are cases though where, sorry, there you go. Point out the pool size, the weight. So you want that one to be your highest weight. Your limits, you don't want to set this any higher than what your savings plan is for, because once you're past your savings plan, you probably want to try to leverage a cheaper node, which is, in this case, probably not going to be C4. I'd want a newer instance, and I would want to leverage Spot. So just make this is just for your savings plan. Anything else, you want it to go to a different pool. But just because this has the highest weight does not necessarily mean that your pod will go into this pool. Your pod may put you over the limit of the pool, or your pod may just not fit into a C4. You know, you may have other restrictions on there where you need higher network or something, and it's not going to use this. So this isn't a guarantee. It's just this is the best estimate to try to use this first. The other restrictions I have in here, like I said, it was C4, which I don't hope no one's using C4, but example. And in this case, like I said, is the other one, it's AMD 64. And this one, this important part is this pool, you want it to be on demand only. You don't want it to use this pool and create a spot node, because that's not going to count towards your 20 CPU commitment for the savings plan. The next part of that would be setting up a separate pool for on-demand or spot. This one is probably going to be the pool that you have that has the most capacity. In this example, I have it as 200. That's probably, everyone's different, probably not going to work for you, so don't do that, but it just needs to have a lower weight. So the weight on this one is 50. This one, it is for AMD 64 and ARM 64. This part is a little bit trickier because this is the ideal configuration, is you want to be able to support both. But if all your workloads don't have an image that can run on ARM, you need to restrict it somehow. So either you need to make sure that you go through and update the affinity for all those pods, or use a tool such as like KubeVirt or something, where if there isn't a if you don't have architecture specified in your affinity, you're automatically adding it. AMD 64 is usually pretty safe, but not so much for ARM. But ideally, you want everything to be able to run on both. That's going to give you the best chance for savings. In this case, I'm explicitly saying that I don't want it in, I don't want a T node because I don't want any credit-based nodes. I don't think that's a good fit for Kubernetes, and I just wouldn't want to use it. And all these requirements are basically, all of them have to be true for you to be able to, for it to get a node. So it has to, in cases, it's going to be an or AMD 64 or ARM 64, and it has to not be a T node. I don't want one of these smaller nodes, like a nano, a micro, a small, or a medium. This is going to be very dependent upon what you have. But when Carpenter is going to calculate the overhead for a node, It's going to look at all the daemon sets, just the kubelet overhead, and see what's left, can what I need to schedule is going to fit on there. If you end up going too small on these, you're going to get a node, and it's going to fit like one pod. So most of your overhead is going to be daemon sets, so it's kind of a waste. Very, very specific to your setup, but you want to make sure that you are restricting some types. I personally, my setup doesn't match this one exactly. I'm also restricting just some types in general, nodes that just don't work well for me and would not make any sense. And like, I kind of skipped it here, but right below this one, I'm skipping specifically C4, M4, and R4. The reason I did that with this setup is I wanted this to work for some GPU nodes. And so I'm not doing an instance type, so I don't have M, R, or C listed. So it's going to basically work for every class. It just has to be greater than generation 3. So I could get a G4 node out of this. But if it is a C, an M, or an R, I don't want to use C4, M4, R4. I'd rather use one of the newer generations. So it can be very flexible for how you set this up. And the last bit is, like I said, this is going to work for both architectures. And just you got to make sure that you either are handling that. Otherwise, your pods are going to come up. They're going to go on a node they can't, and they're just not going to be able to start. They're just going to crash. There is some things I probably should cover with this, though. As I said, this one will work for a GPU instance. GPU is very expensive. I don't have to configure a separate pool, but those GPU, that CPU count, right, that limit is going to come out of that 200. And so if I don't have those restrictions on the resource quotas for the namespace, somebody could spin up a ton of GPU with this, right, and it would basically soak up the pool, and it's going to be a lot of money. Those cases, you may want to just create a separate pool and restrict how it's being used with a taint. That's up to you. It can work this way. Carpenter is not going to accidentally pick a GPU node. They're just too expensive. It's going to find a cheaper node or a spot node first, so it's not going to happen by accident. Someone's going to have to specifically ask for it. But you want to make sure you're putting protections in place so that if something does go awry, it's not going to cost you a fortune. So the next case, a little bit more detail on this, would be disruption. I think disruption is really important. Carpenter handles disruption. It's pretty smart about it. It's not going to try to consolidate a node that it can't. So in this case, I would heavily recommend that there's two ways to tell Carpenter really that not to disrupt. You can either use the pod disruption budget, so it has to meet and keep the budget if it's going to consolidate a node. That's the ideal way. The second way would be to annotate your pod to do not disrupt. If you do that, Carpenter's not going to be able to get rid of that node as long as that pod is on there. So I would heavily recommend you only use it for short-lived things like jobs and things of that nature. So I really focus on that. When Carpenter does go to consolidate those, in this particular case, it's going to consolidate whether they're empty or underutilized. When it's only going to do that though if it sees that those pods can go on to another node. It's going to work two different ways for this. So that's the policy, but the budgets are what's important here. It's only going to get rid of 20% of the nodes, but it's only looking at ones that are empty. So if I'm during like a day where I know I scale a lot, in this case, if you have a partially utilized node, it's not going to get rid of it. That's specifically, is that work for you? But it may not be the case. You may want to just remove that restriction and just have it work for all cases. But it's just something to keep in mind. There is another way to configure this. You can have a separate rule in here where you just put a flat count for nodes. And the way that's going to work is it's going to try to do 20%, but if 20% exceeded that number, like say I had nodes 5 there, it's going to restrict it where 5 is going to be the max. It can't break those rules. This second rule is really around covering the cases that the first budget didn't account for. So I only want to let nodes get consolidated, underutilized. This one says do it for an hour after midnight. The drifted case is where Carpenter has there's an update to the AMI and it can swap the node out. So it's drifted from the EC2 node class. It'll consolidate that node and spin it up with the new AMI. Now this is just how it's going to force it, right? If you're scaling during the day normally and the EC2 node class is already updated, those new nodes are going to have the updated AMI. But this is just you specifying disruption to force the nodes that didn't come out normally. And then this last bit is my preference, but everything isn't coded perfectly. There are memory leaks, there are other issues. And this bit right here says that, after 30 days, we're going to cycle the node anyway, just to make sure that we're getting a fresh one. The termination grace period is extremely important if you use that setting, because Carpenter is going to try to consolidate that node, but if it has do not disrupt on it or something else, it's just going to hang around and it's going to have one pod on it forever. And so the termination grace period is basically how long that pod has to just finally come off there before Carpenter's going to go, all right, I'm done with you. We're going to get rid of this node anyway. So it's just going to kick it off. I would recommend that. This isn't required, but I would still recommend it because, like I said, there's always some issues. So, and I've definitely ran into memory leaks in the nodes before. I have a little bit more to go over. This bit, previously that was pretty much like how you want to configure Carpenter for saving you money. This is just a little bit of details on how Carpenter is going to pick the nodes. So this is the pod level specification. Carpenter is going to treat your required selectors and your preferred as actually being required. So if, in this case, right, I said I prefer it to be in spot, Carpenter actually treats this as both as required. Once the node's there, or if there isn't any node there, like the scheduler is going to respect it as is. But if I had some other selector here, like say I had, instead of spot, say I was looking for ARM, Carpenter is going to treat it as a requirement because it's actually going to get a new node. So it's going to treat your preferred as like this is what you want. But once the scheduler gets it, it will respect this exactly. I can't tell you exactly why they chose to do that, but if you prefer something and I'm going to go do it, right, I might as well give you what you want rather than this setup, which is just, a best attempt. Well, and that's just the same thing I just said. This one is strange, and I included this here just because this kind of bit us with how we were working with GPU. I don't know if you guys have used time slicing. Kubernetes has the concept of extended resource. So you have your CPU, you have your memory, GPU. With custom resources, you can basically say, like, this node has a network capacity of some value. Even though the scheduler, if their node has that and the scheduler can put the pod there, Carpenter isn't going to know how to schedule those nodes. So it's not going to work for Carpenter. You'd have to have the node already there. There are ways to work around that. Back to when I said that Carpenter has a well-defined set of labels. Even though I can't, see if I can give you an example. Say I have a node that had a gigabit network, and I have two pods that need 500 meg network. Normally, if I had the schedule on there, right, it's going to see this pod needs 500, that pod needs 500, so they know that they both can fit on the node. With Carpenter, you can't do the custom resources. I'm hoping they add it. Instead, what you have to do is just in your affinity for the pod, say that you need a node with a greater than a specific network value. You'll get on the higher bandwidth node, right? But it's not going to make sure that the resource is partitioned out correctly. And how that plays into here is with GPU nodes, frequently you'll see what they call time slicing. There'll be either the NVIDIA device plugin I talked about earlier, or you'll run your own setup where the node normally only has one GPU, but as far as workload's concerned, once the node comes up, that device plugin changes the capacity of it. Now the node has 2 GPUs. Carpenter can't know anything about that. So if I have 2 nodes that say they need GPU, or sorry, 2 pods that say they need GPU, Carpenter's going to end up creating 2 nodes. Each one has 1 GPU each. And if you don't do anything and just go with that as it is, even though the nodes, because I've time sliced them, each one can support 2 GPUs, the pods are going to get evenly distributed, so you're going to have 2 half-utilized nodes. The workaround for that is, and it's not perfect, right, is in your workload you would do a pod affinity selector so that you prefer to be scheduled on a node where one of your pods is already running. What that's going to do is Carpenter's still going to unfortunately start up 2 nodes. They're going to update to say that there's 2 GPUs on each one, but the scheduler is going to see this and it's going to put both pods on one node. And then what's going to happen is the other node is underutilized, so Carpenter can consolidate it. So there's still some waste, but it's better than only utilizing half of each node. Does that make sense? I hope. Like I said, it was my specific case, but I feel like with the way that AI is coming along and a lot more GPU, it's probably going to be relevant for some cases, or a lot of cases. And following these practices, I didn't get this gentleman's name. For our case, right, we had a much higher restriction on what kind of node we could run on. And as of December, I think we had 500 GPU nodes, and we had about 67% were able to go on Spot. However, you can't count on Spot because with the way AWS works, they can take it away at any time. You get a 2-minute warning with Spot, and Carpenter can work with EventBridge, and you can have those messages go into a queue. So that way, if you have that 2 minutes, it can try to consolidate, prepare to consolidate nodes. So the node will get cordoned, and those workloads can get moved. What was I going to say about that? Sorry. So that's how you can handle the Spot disruption. I would still prefer to go on Spot, but you're going to want to be prepared. Like I said, it'll fall back to an on-demand. If you do really have those really expensive workloads, what you're going to want to do is, if it's like a Kubernetes job or something, look into something like, there's a product called Q, and you can kind of throttle those jobs and preempt them, so that way your number of pods doesn't just massively spike. It's kind of more flat throughout the day, and so it can try to leverage Spot more. I did not do that, and like I said, I had 500 nodes, and it was 67% of them were on Spot. January rolled around, and I think I killed the Spot economy for everybody, and I dropped down to 6% Spot usage, and it was not a fun time. Like I said, though, my case was specifically, it was for a very particular GPU. But if you're following the practices where you're just being as flexible as possible with what kind of nodes, like my first example where I said I can use C, M, and R, and didn't really put in too much beyond that, the more flexible you are, the more likely Carpenter's going to be able to find a Spot node for you. And that's really the key to being able to get available Spot. My case, I needed a G6 extra large, and my stuff could only work on a G6 extra large until there was work done on the workload to be able to support other node types. So I was really locked into that one, which is, like I said, that's why I killed the pool, is because I was only getting that one. Ended up being very expensive. So be as absolutely generic as possible. If your workloads can be on Spot, you want to run them on Spot. I would suggest trying to put Spot in your main pool, but if you have to do a setup where you split it off as a separate pool, either put it as a lower priority and have workloads specifically ask for it, because if it's lower priority, it's going to use the higher level pool first, or you're going to want to put a taint on it and have your workloads that can run on Spot tolerate it. Spot is not going to be a very good fit for some workloads. There are some tricks if you want to kind of try more for a balance. If you want to run, say, like 80% of your pods go on demand and a smaller subset go on Spot, there are tricks for that. They have, I didn't put it in here. It's on the website, Carpenter's website, where you can basically kind of set it up and do it with selectors. I tend to not, I prefer to stay away from that simply because it's very specific use case, right? Because you have to do that setup for every different flavor you want. Like if this team wants to run 60% on demand and 40% Spot, but the other team says, oh, we need 80, it's going to be, you're going to have to duplicate that setup. So I prefer not to go that way. But whatever you have to do to get your, your stability and get your cost down, I mean, it's probably worth it in that case, depending on how big the workload is. So I wouldn't be completely against it, but I prefer to do as little as possible and spend my time and money getting, either another engineer or, SaaS product so I don't have to maintain something else. I ran through this really fast, so I guess I just have Q&A, and I'll probably miss something. So if you have questions, please ask me now or afterwards.
I have a few questions. Maybe I'll
Yes.
When you were showing the instance type rule set that was fairly complicated, you had, maybe 5 or 6 different rules to limit what set of instances would match against your Carpenter node pool.
Mm-hmm.
Is there some sort of like dry run or like something you could say, like if I were to ask this for this node, for this node pool right now, which instance types would actually fall out?
So are you referring to this one?
Yeah, that one. So like, you said there's like 700, and it seems like Carpenter would know the 700, and you could basically go, of those 700, these 300 fall out, something like that,
So you're just wanting to see the types that it could select from?
Yeah, just to get a general idea that the rules that I'm setting are correct before like sticking it into an actual node pool.
I don't know of any dry run capability. They do have a listing on their website of basically all the types and the labels that they're going to use, so you can kind of use that as a reference. If you wanted to, it's not a dry run, but what you could do is just add a taint to this and just do the smallest, pod possible with a toleration to test it. And if you really want to do it that way, you could probably remove the on-demand so that whatever node it's going to get, it's as cheap as it can be, and it's going to be, a Spot, but it's not going to tell you,
That's more like a sampling,
Yeah.
though, instead of a overview. These are the set of instances that I will match.
Yeah, it doesn't support it that I am aware
Okay.
of. I'm sure there's a way you could probably calculate it. There's probably a tool out there for that, especially because I said they have all those labels listed.
Yeah.
Because you're going to find a label for pretty much everything.
Okay.
It's architecture, CPU, who the manufacturer is. So these, like GPU, if you do want to leverage GPU and you need a specific type, I would recommend against like specifically asking for that instance type. And instead, Carpenter has a label where you can just tell it the architecture you need. So like if you need L40 or L40S or Ampere, there's labels for all of that. And so that'll give you, Carpenter can go, oh, well, here's all the instance types that support that. So, it'll be easier for you. But yeah, there have to be a tool for it that I'm not aware of. Sorry, I don't have a better answer.
Yeah, I was just thinking because Carpenter has to be doing that math for you while it's running. If it could just do it up front and tell you these are the selection. Okay.
I will say they add a bunch of instance types all the time. Before, it was just the AMD and, NVIDIA. Now there's the V1T. There's always new stuff. So even if that was the case today, it may not be the case tomorrow, which is, as far as your node pool setup, I would recommend you be as flexible as possible. And on the pod side, just make sure that you're only as explicit as you need to be to ensure you run, and keep it as flexible so you can save the most money.
Nice talk. I think you covered this briefly, but I think I missed it. So spot instances don't count towards your like savings plan or reserved instance spend. And I think you had like some, like Carpenter doesn't know what your reserved instance or like what your savings plan is, right? You
Correct.
just set up your node pools so that it like matches whatever you've purchased. Is that right?
Yes.
Okay.
Yeah, which is why in here I said, I want to be explicit that you put this one as on demand, and this one you want to make sure it has a higher weight than the other ones, so that you're trying to make sure that you're at least meeting your capacity you want to make sure you're at least meeting your commitment for the hours, and that limits 20 CPU. Like I said, just make it as at most as big as your pools. This may be a little complicated setup depending on your your account, because like you may have a dev account and a prod account, and if you have multiple clusters in each, well, how do you really find the balance where you're not over like you don't want to do your savings plan on each cluster, because now you've done 5 times or whatever it happens to be on demand when you really only did it at once. So you're really going to have to try to like play with that and figure that out, so you're not doing any more than you absolutely have to.
I'm a big fan of all the things that you said. One thing that I'm unclear on is over provisioning for startup time.
Oh, I did not cover that. Generally, you probably don't need to do over provisioning. And over provisioning does work with Carpenter, but it's a better fit for cluster autoscaler. And the reason I say that is the way I've always done over provisioning is I'll have a deployment, and I'll have like a pause image that doesn't do anything.
Yes.
And I'll tell it, do you guys use Kita, or do you guys just, okay. No. Kita's great because you can tell it, I only want to over provision, this day during this time frame. I mostly only use it on my CI system because I know there's going to be a lot of jobs coming up.
That scales up and down a lot, yeah.
Yes, but the reason I only use it only with my CI system, right, is because whatever node it's going to provision, it's a very explicit case, and depending on whatever workloads you have come in, right, it may not be the fit that's best for those. My CI, I'm using GitLab, so like I know it's going to be AMD 64 in this, and I know the minimum size, so it works better. So if you're going to over provision, it's probably going to be for a very specific like spiky workload that you have to account for. In that case, you can do it because you know what kind of nodes those need. But other than that, it doesn't work as well with Carpenter.
That's what I was thinking too, because you can't, like, when you have a heterogeneous pool of nodes, then how do you say I want to have like an over-provisioned half of a node that's evictable? Because you have to give those in like, you can't say 50%. You have to say 16 gig or 32 gig or whatever. So
yeah. If you're doing it in that case, right, you're probably doing it so that it's just, it's going to be on like the only pod probably on the node.
Yeah.
And it's the normal cases though, if you do it, like you just want to make sure it has a lower priority and it's it can be preempted. But yeah, it's definitely harder with Carpenter, but you're saving it on not being so explicit. But Carpenter is so much faster because it's dealing with the EC2 Fleet API instead of the auto scaling group that I really haven't seen it be an issue. But in certain circumstances, probably more so if you have pods that are like some workloads that are just really slow at coming up, that extra little bit of time for a new node may just put you over the top. And so, yeah, those cases, it's going to be explicitly for that workload.
Another question I had was, I am much more familiar with Cluster Autoscaler, and what's the visibility of the things that Carpenter is doing or planning to do? Like with Cluster Autoscaler, it'll add those like node annotations. Hey, this is a deletion candidate. Is there the same thing with Carpenter or similar?
Yeah, Carpenter's still going to add the same or similar annotations, so you'll know. The one thing I didn't go over for CRDs was the node claims. So it's it's Carpenter's claim on a particular node. That node claim will match the annotations Carpenter's going to put on the node. And the logs are pretty good for you being able to find stuff. I dug in them through a lot when I tried to figure out why did I go from 67% spot to 6% spot. And I was like, why is this failing all of a sudden? And then, I looked and it's like, oh, the disruption was really high and there's just no nodes available. I used them all. It's really good for that, and the metrics side of it are really good. Carpenter is, depending on your setup, it's a little bit more memory heavy than I would like. I would say it's still probably less than Cluster Autoscaler, which keeps everything in memory. But the metrics on it are pretty good. And that's the only issue I've really had with Carpenter, was that when I first started up, I just started putting so much more on there, and I'm not running VPA, so I didn't go back and adjust the resources. So I did have it kill itself a couple times. That's the only issue I've had with it.
So Carpenter has problems managing its own scaling.
I mean, that really falls into the pod scaling, not the cluster scaling. But yeah, I would say I had a problem with it. I think Carpenter was perfectly fine.
I was just going to say the recommended configuration from Amazon is that you run Carpenter on a Fargate node so that it doesn't scale itself.
Oh, yes. Yeah, Carpenter definitely. There is a separate label for that where you want it to go in your managed node pool that you first set up your cluster. My setup, and probably the one most people will use, is you'll have like a minimum number of nodes, probably like 3. So you have the AZ spread. Carpenter, you want it on those. You don't want Carpenter on a node that it manages itself. That's a recipe for disaster. I mean, I'm here regardless. So we can just stand here and stare at each other. I'm sorry. I have a terrible sense of humor.
You're fine. The idea that Carpenter's going to pick the cheapest node type makes me think that it will. You had the slide where it was like, I have these pending pods and I have some unschedulable pods, and Carpenter will look at the unschedulable and figure out what's the instance type I need for those. Is the idea, what that feels like to me, like my knee-jerk reaction to that is that you'll always end up with like the smallest instance types, and then you might end up with, oh, I have a couple pods that are unschedulable, so I get a small instance, and then a couple more, then that's another small instance, but then the daemon sets start adding up. Is the idea that you eventually get to the point where they get consolidated into larger nodes, or?
It's really going to depend on how you set up the pool. Like I said, I restricted those several types. So it really depends on that. But Carpenter's all about, just-in-time launching of a node, so just the minimum of what you need. If you're scaling, like if it's, I'm trying to think of like, when does all the tickets and concerts and everything go on sale? Tuesdays? So like if you were doing something with that, you're probably going to be doing the over-provisioning thing. But yeah, it's really going to just pick the smallest node. Depending on the flux, it may not be a big deal. But in that case, you're going to want to, like I said, just make sure you're excluding those smaller types. If you're, I don't remember your name, sir. Sorry. We were talking about Argo earlier. I use Argo to deploy everything, and I love it. And one of the things I love about Argo is how easy it is for me to just, deploy to every different cluster without having to do a lot of work. You're going to be able to have more control over, now you could probably do it with anything with Helm, but more control over like what those values are. There isn't really any shared templates that I know of for writing a node pool. I have one for my setup, and it's really simple to do, but like if I'm my dev environment, right, I probably can be more acceptable for those smaller nodes, but it's really easy to control that, and it's really easy to, set like your subnets and things like that. And Carpenter will do that automatically for you. I didn't show it in here. I thought it was kind of probably easier to figure it out looking at the documentation, but figuring out through selectors what subnets it should use. But if you have some that don't follow the rules, you can do your own. But I would just restrict those node types based off of the environment and what you need. I think we have 8 minutes left, so.
One of the things that Carpenter does that I'm not used to is I am used to the ASG, separate ASGs model. And you said, oh, you don't do that. It just makes EC2 nodes directly. Do you just go, the node pools are still like they're in the EKS dashboard instead to sort of see how many nodes, like the thing that is not an ASG anymore is visible in the EKS Amazon, the AWS dashboard?
No, it's not going to be.
Okay.
Because I don't ever use that, to be honest. If I remember correctly, that's just showing you the groups that you have that you've created that are managed, which would have the ASG. And so this isn't using either of that, so it's not going to show up there.
Okay.
So you would, if you needed that information, you would most likely get it from the metrics Carpenter is exporting. Yeah. Or you could, search by the tags on the nodes. Okay. Especially if you're doing a setup where you have a couple clusters in the same account, you would end up having to do it that or use the metrics to do it.
The only other thing, we looked at Carpenter and didn't move to it yet, but I still would like to. Our main thing is that we have a set of pods across a few availability zones like you should, and we're using EBS for our EBS storage with CSI, and often when we have unschedulable pods that we're using a PVC, cluster autoscaler will make a new node in the wrong ASG because it has no idea about what the thing is, and my understanding is Carpenter actually takes that into account when it's looking at the pod scheduling.
Yeah, Carpenter will look at that on the pod and make sure that it goes in the right AZ. It used to not be as good at that, but since they've hit version 1, I haven't had any issues with it. Now, you said CSI, so I'm assuming you meant pod level storage, right? For EBS? Yeah, that's honestly, that's probably another big thing I didn't even think about with this, right, is that you're going to get the node in the right AZ for that, because already reattaching an EBS to a node is already kind of slow. Yeah. And so, yeah, you wouldn't want that. Unfortunately, even the over-provisioning you were talking about is not going to help that. That's just going to be an extended amount of time, which is a bummer. Oh, and I didn't mention it, but everyone should do this. Make sure you set resource requests on your pods. Like Carpenter needs to know what you're using for it to pick the right node, so it's not going to do a very good job of doing that. There's nothing to keep you from running Carpenter side by side with Cluster Autoscaler, and you can slowly move your workloads over to Carpenter. I think that when I first set up Carpenter, I had the whole thing done and moved over in a couple of hours. It's really simple, and figure if a schmuck like me can do it, I think you guys will be all right. But yeah, you can totally transition to it over time, and pick a lower environment, dev or stage or your CI system or whatever you want to do to try it out, and see the savings. I don't know what you guys are using for savings. There's plenty of tools out there if you want to use OpenCost or something, and so you can kind of try to track your savings. But if you follow the rules of being more generic, like I said, I'm pretty sure you guys will get pretty significant savings out of it. Just don't ask for a very, very specific instance type unless it's for a savings plan.
Okay.
Yes.
So since we started talking about the savings, right? Kubernetes is claiming to be very cost effective comparing to cluster autoscaler. Do you have any numbers, like for example, you've been able to cut down like 50% of your bill or 30% of your bill? I would be happy to hear about that a little.
So it's really hard to say, if you're able to do a savings plan, if you're super specific, I don't believe the number they say it's like 90% or something silly like that. I think I saw 58% for my stuff for a savings plan.
Mm-hmm.
But to use a savings plan is, it's an hourly commitment. So, middle of the night, right? Like that's like your lowest, the least amount of nodes you have. That's probably all you're going to want to do for a savings plan. You just want it for to cover the bare minimum. Because if you go over that, you're paying for it whether you use it or not. But if you're super generic on the node pools, you should be able to always get spot. And I think when I first switched over for GPU, I was getting like 70-some%. And like I said, there was 67% of mine were on GPU. But that was with me, getting 500 nodes on a Sunday, and then running them on spot and then getting rid of them. And now it's don't get spot for GPU 6 in US West 2. It's going to be a bad time for you. You're not going to get a node, and it's going to be expensive. I'm sorry for everybody that needed that.
Thank you.
Well, thank you very much for a super informative talk.
Thank you, guys.
And have a good night. Game night has already started, I believe. And see you back here tomorrow for more great talks about cloud native stuff and other stuff.